I think the most interesting part was that we have seen people from different parts of the world, especially researchers who come from different disciplines, from different countries.
I hope GYSS, which is a borderless community, can keep growing to influence more people, connecting the top scientists and young researchers.
Found out that it's nice to communicate with young, educated people who can ask very unusual questions which you have never thought before. They also kind of see that Nobel laureates are just normal people, and that allows them to get inspired to achieve the same heights in their future career.
Education to science is extremely important for people and extremely important for countries and for our health and for our wealth. And I think that GYSS is one important tool to disseminate this spirit around, attract young people and increasing the spread of knowledge in the society.
The way that it brings together scientists from around the world, young scientists, students, is rather special. They often had the same questions, the same concerns, the same desire to be able to contribute to the scientific process.
So GYSS is as relevant today as it was 10 years ago. In fact, more relevant than before. I hope that GYSS will continue to engage in this important mission so that young people everywhere throughout the world will have this opportunity in order to get together to tackle and solve difficult challenges.
This year, GYSS celebrates its 10th anniversary of the annual meeting between young scientists and engineers from all over the world, and outstanding scientists and engineers who got Nobel Prize, field medals, Millennium Technology Prizes, and Turing Awards. Last year, besides the problem of COVID-19 pandemic, I had a severe accident, and so I could not join the event even online. This year I can be with you online, and I am allowed to send more Thai young scientists to the event than the previous years. Besides having the opportunity to learn from global scientists and engineers from other young scientists and the visits to research institute in Singapore, these young people who are mostly in science and technology careers can be inspired to create the works that benefit Thailand and the world. As they become successful professionals in science and technology, that will inspire other children to pursue the same careers. And the government could see the importance of promoting more citizens to study science and technology. I hope that young scientists and researchers in science and technology won't be discouraged by the obstacles they encounter and continue to do their best. I hope that they will always think of new things as GYSS moves on to the next 10 years.
It's 10 years of Global Young Scientists Summit, and it's my pleasure to congratulate Singapore's National Research Foundation and also the organizers for having GYSS this year, and I wish you a wonderful meeting. I'm very glad when I'm thinking of all the participants being the current or the former ones, because having exchange about science is one of the best things you can do. We in Lindau also had an anniversary last year, and of course it's always great to have this recognition for the past, but at the same time it gives much motivation and energy to carry on, particularly in times like these. Thinking of the young people, my message for you, young scientists taking up a career in science and technology would be: do what you're really passionate about, be always curious and ready to share your knowledge, and a platform like the Global Young Scientists Summit is great for doing that. Sometimes I'm asked if I could get advice. I'm not within science, but my advice for further careers, of course with reference to a Nobel Prize, would be: despite all very obvious value in applied sciences, let's take COVID-19, do not lose sight of basic research, also for the sake of future generations. And now I hope you enjoy the GYSS 22 and wish you all the best for it. Many greetings from Lindau.
The success of the Global Young Scientists Summit is a testament to the importance of borderless collaboration in the pursuit of excellence and the benefit of humanity. As we seek to tackle global challenges such as climate change, biodiversity loss, and protecting human health, and to pursue the knowledge of ourselves and the universe around us, this is the bedrock of future research, and it's your generation that will be at the forefront. The scale of these challenges may have inspired you all. I'm sure the desire to expand our understanding and make the world a better place will continue to inspire your generation. While the challenges are great, your generation, like those before you, stand on the shoulders of giants. You have access to new knowledge and tools that can help change the world for the better. I urge you all to grasp the opportunities and pursue your passions.
The Global Young Scientists Summit, GYSS, was established 10 years ago in order to excite, engage and inspire young researchers to pursue their passion, develop solutions in order to solve problems in our economy and in society. This has never been more necessary. For example, COVID-19 has impacted all our lives, devastated many economies, changed our social habits. In addition, the world faces existential challenges, two of them, climate change and environmental sustainability. If we are to have any opportunity or any hope of overcoming these challenges, we need fresh minds to think up novel solutions, consider out-of-the-box avenues, and be able to put together a coherent program. What GYSS has done is to enable these young minds to collaborate together, exchange views, and form a community which will give us some advantage in overcoming these issues. GYSS has done well the last 10 years. I believe that GYSS will continue to do well and will continue to engage our young researchers and inspire them to do great things. Congratulations to GYSS on your 10th anniversary. I believe GYSS will continue to be relevant and will create new challenges and opportunities for all our young scientists and benefit the world and the scientific community. Congratulations.
So good morning, everyone. Welcome to the plenary lecture this morning. It is a pleasure to introduce today's distinguished speaker, Professor Bảo Châu Ngô, or simply Châu as to those who knows him. Châu is a Vietnamese-French mathematician at the University of Chicago, best known for proving the fundamental lemma in the Langlands program. He is the first Vietnamese national to have received the Fields Medal in 2010. Châu became a professor at Université de Paris-Sud in 2005 at the age of 33. That same year, he received the title of professor in Vietnam, becoming the country's youngest ever professor. Since 2007, Châu has worked at the Institute for Advanced Studies at Princeton, New Jersey, as well as at the Hanoi Institute of Mathematics. But since 2010, he joined the mathematics faculty at the University of Chicago. He also served as the scientific director of the newly founded Vietnam Institute for Advanced Studies in Mathematics from 2011. Châu first came to prominence by proving in joint work with Gerard Lemong the fundamental lemma for unitary groups. For this work, Châu and Lemong were awarded the Clay Research Award in 2004. In 2008, Châu eventually succeeded in proving the fundamental lemma for Lie algebras, together with results from Jean-Luc Wasperger, who had earlier deduced stronger forms of the fundamental lemma. From this result, this completed the proof of the fundamental lemma in general. Chou's proof of the general case of the fundamental lemma was selected by Times as one of the top 10 scientific discoveries of 2009. Among the many honors that follows, he received the Fields Medal in 2010. And in 2011, he received the Legion of Honor from the French government. So without further ado, let's welcome Professor Bảo Châu Ngô to deliver his plenary lecture this morning.
Hello, my name is Ngô Bảo Châu. I'm professor of mathematics at the University of Chicago. I'm very happy to be invited to GYSS this year in Singapore, virtually. So what I would like to talk to you is about the Riemann zeta function and its generalizations. So it's very central topics in number theory and in mathematics. It's been driving a lot of research in mathematics currently. Although we start really back to mathematical antiquities. From the day of antiquities, Greek mathematicians and philosophers were only very puzzled by the prime numbers. And one of the some discovery they made that there are infinite many prime numbers, and they proved it rigorously in Euclid books Elements. I'm not going to repeat that proof, that beautiful proof based on the proof by Absurd. But actually, I want to move very fast forward time, I think classical period, where in which the Swiss mathematician Leonhard Euler gave a beautiful analytic proof. So Euler started this identity. When you see the screen, on the left-hand side, you have the infinite series, sum from n to 1 to infinity n to the minus s. On the right-hand side, you have the infinite product over prime numbers. The factors are 1 minus p to the minus s and the whole inverse. You can prove the identity very formally because when you expand the factor on the right-hand side, you get some infinite trigonometric series, and you can equate them by terms by using the fact that every natural integers has unique prime factorizations. But that is the, however, a non-rigorous proof because we first had to establish convergence before dealing with infinite sum and infinite series. And indeed, in this case, both the left-hand side and the right-hand side are absolutely convergent for any real numbers s greater than 1. and not convergent when S is smaller than 1. That we learned from the first principle in analysis. And and now you see that the main focus is on exactly on S equal to 1. When S equal to 1, on the left hand side you have this the harmonic series, and which is the sum of n inverse of n, which is not convergent, which is divergent. Whereas on the right hand side, if there are finally many prime numbers, it's obviously convergent. So if you assume there are finally many prime numbers, we end up into some very contradictions. That was Euler proof. We start with the fact that every integers have unique prime factorization, and by passing by analysis, by the divergence of the harmonic series, we arrive at the conclusion that there are infinite many prime numbers. And in this, you see that actually these identities for the Euler product play a fundamental role in the studying prime numbers. So this is the second slide, and where this function is what you call the Riemann zeta function. Although that was Euler who the first introduced it. So what Riemann did is look at the same sum, n from 1 to infinity of n to the negative s. But now instead of s being a real numbers, we might think about it as a function of complex variables. Now s is a complex variables. So what changed? So on when the real impact of s is greater than 1, nothing changed. Here you can have a absolutely convergent series, and this series can be have the Euler product, is product of on prime p of the Euler local factors 1 minus p to the minus s the whole to the minus 1. But what is very interesting is when you think about complex variables, is that this function can be analytically continued. That you can extend, you can prolongate the function zeta on the whole complex plane. With of course it keep having a points at s1 to 1. Right? So for instance, then you can speak about the value of zeta function when s1 to 0, for example, then you get some kind of magical identities that the mathematicians in the classical period are very fond of. You get some like when s1 to 0, we had 1 plus 1 plus 1, etc. It seems to be equal to the value of zeta at 0, that is minus 1/2. And you take s equal to negative 1, it's even more curious. You get the values of zeta at negative 1, which is negative 1/12, is 1 plus 2 plus 3 plus etc. Of course, it is just this is nonsense identities. 1 plus 2 plus 3 plus 4 is just a divergent series. It is not equal to negative 1/2, but however, there is a way to think of 1 plus 2 plus 3 as if it is negative 1/12 if we see this in families with s changing, and s become negative 1 and zeta of negative 1 is negative 1/12. So that is the very when Riemann introduced these complex parameters, then you can make sign of this infinite series even for the values of s where the series is not convergent. So that is this series bears the name of Riemann. So in keeping studying prime number p, it's actually a very interesting thing to instead of studying zeta function itself, to look at its logarithmic derivative. That is zeta prime of s over zeta of s. And when you expand it, you get a sum, again, infinite sum from n 1 to infinity of lambda n over n to the s. where lambda n is called von Magogne function, which is equal to log p if n is a power of p and 0 otherwise. So, for example, lambda of 6 is going to be 0 because 6 is 2 times 3. So we only keep the values n prime or square wave prime or cubic power prime, etc. So on the right hand side, essentially you get a sum over primes and the power of primes. And that is how you can study the distribution of prime numbers. So the prime number theorem, that is one of the big theorems in number theory, that's saying that if you count the number of prime numbers less than or no more than some given real number x, positive number x, then as x goes to infinity, pi of x is approximately x over log x, which means that the ratio of pi of x and divided by x divided by log x in 10 to 1 as x goes to infinity. And so that is actually the subject of the papers, the only single paper that Riemann ever wrote on number theory, but really marked the beginning of modern number theory. And his papers is on the number of prime less than a given magnitude. So you want to have estimate asymptotic behaviors, understand asymptotics of this function pi of x. And it's actually not very difficult to see that instead of counting pi x, that means assign 1 to x prime numbers and 0 to other numbers, you can change it into some other function like lambda n, the von Magogne function, which is more related to the Riemann zeta functions. And it is actually can be proven by the elementary means that the prime number theorem, that pi of x is equivalent to x over log x is equivalent to the factor sum of lambda n and n less than x is equivalent to x. So that so instead of just counting prime numbers, we're going to count with weight given by the von Magogne function, which is equivalent and which is more accessible by analysis. So in general, when you look at some Dirichlet series, that the sum of n to the minus s, but weighted by some arithmetic function, a of n, and we assume that this series can converge when the real party of s is greater than something like sigma 0, then by the Perron formula, you can see that the sum of an, so this arithmetic function an, can be computed by the integrons of the function GS over some vertical line, right, when it is after convergence. And now the trick to estimate this sum is going to use analytic continuation. So instead of integrate on this line, we are going to move the integration line to the left, to the area. As you know, the further you can move, the better the estimate you can get on this sum of arithmetic functions. And so assuming that the function g of s has a meromorphic continuation, and you can push integration length as far as possible, then you can obtain that the fact that this sum of an, like the sum of von Magogne function, can be estimated in terms of the points of the function g of s. So by this thought, I think this is basically the ideas, the big idea of Riemann. You can estimate that the points of the log, the derivative logarithmic of function zeta, is have single component as 1 to 1, as much as function zeta, and it have if we know that there's no if zeta has no 0 on the on the line of Riemann positive h1 to 1, then we can actually prove the prime number theorem by this the principle I just explained. But if you can push this further, not just a little bit away from the line h1 to 1, but go to further, to the critical line Riemann positive h1 1/2, then you get the best, everything you can say about distribution of prime numbers. So that is what Riemann did. He proved that the Riemann zeta function can be analytically continuous on the whole plane. It has functional equations, and he conjectured that on the zeros of the zeta function, and which corresponds to the points of the D log zeta, lie on the critical line of the s1 to 1/2. So Riemann zeta conjectures on the zero zeta function is certainly the most well-known and for the most important conjectures, standing conjecture in prime number theory. And if you ask any number theorists what they really want to prove, I mean, they can dream to prove, it probably will be a Riemann zeta conjecture, Riemann conjecture of zeta functions. So that is my very brief story on the Riemann zeta function. We start with this this Euler's product, express the sum of n to the minus s as the product of the prime p, and we are introducing s as a complex parameters, and following Riemann, you can prove that the function zeta of s, which a priori undefined when the Riemann property of s is greater than 1, you can extend meromorphically, you can continue meromorphically zeta s to a whole complex plane. The function is unique point at s1 to 1, and more of which actually satisfy a beautiful functional equation. Zeta of s is the related zeta of s and zeta of 1 minus s. And the prime number theorem, that is how many prime less than some given magnitude is can be approached by finding the points of the logarithmic derivative of zeta, because this zeta prime s over zeta s is can be expressed as the sum of the lambda n over n minus s, where lambda n is a von Markovern function that basically counts prime numbers. So by this Perron formula that express the sum of an with n less than the magnitude as some integral of the function of this complex analytic function on some vertical line, and then you can pushing the integration line to the left. You can have very good asymptotic expression of the sum of an if we know the location of the point of the function g, in this case of the d log d zeta. And so the points of the logarithmic derivative of zeta corresponding to the zero from z zeta. So that's why we really want to know where are the zero of the zeta functions. And the Riemann conjectures that they are, except some trivial zeros of the negative integers, they are all located on over the of the Riemann line of symmetries at the Riemann property of s even 1/2. And now let me discuss some very related function that had to do with the question to count prime numbers in some given arithmetic progression. So for that, we fix some integer n called a conductor, and fix some character of the group of z mod n z star. For example, n equal to 3, You can take chi of n is 0 if n is a multiple of 3, and 1 if n congruent to 1 more 3, and negative 1 if not. And then you can form the Dirac L function, the very similar looking sum of n to the minus s, but now weighted by this directly character chi of n, and the same proof as Riemann for Riemann zeta function. One can prove that this function, Dirac L function, can be continued holomorphically, because there's no points over a whole complex plane, and also satisfy a functional equation relating s to 1 minus s. And Dirac also proves that infinite many prime numbers in this arithmetic progression from even the fact that this function has no point equal to 1. So one can ask how it is a simple. Can we have other functions like Riemann zeta function or Dirac L function, which are obviously very prominent piece in the classical number theory. So when you move to the 20th century, when we start studying a very beautiful object, the modular forms, the first invented by Henri Poincaré. So modular form on the half plane, complex half plane, H of real party of imaginary party is greater than the positive. It satisfies some kind of symmetry that F, when you apply AZ plus B, CZ plus D, then they're essentially unchanged as you have achievement the change is given by this simple factors called the modular character CZ plus D to K. And for A, B, C, D, some integral matrix. And such form will have Taylor expansion because of, for example, if gamma is all integral matrices, then FZ can develop into some Fourier series, so AN to the exponential 2IP and Z. And then you can also consider this Dirac series by taking AN to n minus S. And what I discovered Hector, this Dirac function, Dirac series, also have meromorphic continuation and satisfy the functional equation very similar to the Riemann zeta function and Dirac L function. And this is this astonishing fact has really driven a lot of studies in mathematics in 20th centuries. What to understand the phenomenon, how to relate the Riemann zeta function, Hector L function, and so on. So this is the that I wrote the more precise functional equation for the zeta function. If we need to modify zeta function by some gamma factors, here precisely the gamma of S over 2 and which S, and then we get this function. It could be symmetrical. When you flip over the axis of Riemann particle 1/2, and so you need to add some additional factors to have a perfect functional equation, and to do the same for the Dirac function, but now the gamma factor is slightly more complicated, and also have other factors related to prime dividing the conductor, for example. So we really want to understand how we can establish the general theory of zeta function, L function, and that become one of the first motivation for the Langlands programs. But let's come back to the of Ted Davis, one of the cornerstone development model number theory So in Tate developed the theory of Riemann zeta function and include also the DKL function based on the Fourier analysis on the Adeles. So the Adeles, so you start from a field rational number Q's, and as you know, it's not completely easy to understand what real numbers. So real numbers are the way to complete rational numbers so that on Cauchy sequence converges. So that gives you real numbers. But if you have the change the distance, usual distance to the periodic distance, the two numbers are close. If the difference is highly divisible by some prime p, then the compression will give rise to a new local field, called the field of periodic numbers. And it's not very intuitive, but actually it's very fundamental to put on together ring of Adeles R and on the QP. And here I because these lectures I couldn't define it properly, so it's not the whole product, it's about the rest of the product. We have to put some condition to make sure that A remain a locally compact, and Q is going to be a compact discrete subfield subfield of subgroup of A. And now by the way Tate proceed is to use Fourier transform on Dion and QP and do the Melian transforms, and these give and also apply the Poisson summation formula to the co-compact discrete subgroup Q inside A, and that gives rise to the functional equation. And in this way, one of the very beautiful things on the different local factors, even the one that actually added at infinities, is very clearly displayed in the Tate analysis of the Riemann zeta functions. So now Langlands is a way to how they have given proposed a very general framework how to understand properly the generalization of Riemann zeta function, of L function, of DKL function, of HKL function, and also the Analytic approach that Fourier analytic proposed by John Tate. So first, Jacques Langlands construct the Haeckel theory entirely as automorphic representation of the group Gn2 of A, the group the matrices whose value is the Adeles. And Langlands define for every reductive group called the dual groups. The dual group is very important in the way that the dual group is somehow classified representation of the groups. And so for every automorphic representation of G and every finite dimensional representation of the dual groups, Langlands can define some L completely very general L function depending on the automorphic function pi, the finite dimensional representation rho, and a complex parameter S as all a product, very much in the same way as in the original Riemann zeta function. And now the question is, of course, so this definition really encompasses on the known L function before, Riemann zeta function, DKL functions, HKL function, and so on. And it gives the great generalization of that. But the question, the very important question is how can you prove that this L function satisfy the same properties as Riemann zeta functions? For example, one can prove it in metamorphic continuation and prove a functional equation. So that still remains some of the most important questions in the Langlands programs. So the important case known is due to Riemann and Jacques, who generalized work of Tate. In the case of G equal to GLN, the group full general linear group, and rho the standard representative of the dual group of GLN, which is GLN itself. And so Langlands, in his really landmark papers called the Problem Automorphic Forms, proposed a couple of conjectures, which he posed definition of random dual groups. He posed definition of automorphic L function. He put conjectures, pyromorphic continuation and functional equations. But then he posed another conjectures, which is very much in the way, in the continuation of this, called the factorial conjectures. And I cannot explain here the exact content of these conjectures, but he roughly say that all automorphic L functions are the standard L function of GLN that have been constructed and studied by Goldman-Jacquet. So that been reduced, the factoriality conjecture to reduce the general case to the standard case that's been known to the usual Goldman and Jacquet. So another pillar in the Langlands program is the Langlands reciprocity conjectures. Let's say that on L function, the zeta function we get encounters in number theories called Haas zeta function that are attached to algebraic varieties are also the automorphic L functions. So that is a consequence of the conjectures, but that is how you can phrase this in terms of L functions. So that is very important because, for example, in the you sort of have heard about this great achievement of mathematics in the early 20th centuries when Andrew Wiles finally proved the last theorem of Fermat, and he proved it by a very complex apparatus of mathematics using the analytic L function, analytic curves. But for doing that, one of the things you need to prove is that actually what he proved is that the L function attached elliptic curve is also some L function attached to the curve, the modular form that studied by Hecker. And so this is somehow this can be seen as a special case of the general reciprocity conjectures. So this fit very well together, and it seemed to give us through this this concept of L function that come on the way back to Euler and Riemann, a way to connect and deepen a lot of mathematics, analysis, representation theory, representative groups, and arithmetic, the study of differential equation, the study of equation system polynomials, finding solution in rational numbers, and how are they connected to analysis, to automorphic representation through this beautiful but very mysterious concept that has a L function, which are generalization of Riemann zeta functions. And there's a lot of things to do, and I really hope some of you will join us to study mathematics and especially to study Riemann zeta function. Thank you very much.
Okay. Thank you very much, Professor Goh, for the fascinating talk that takes us from Euclid all the way to present-day Langlands. And so here now we are at the Q&A session. I hope the audience have enjoyed the talk. If you have any questions, please send them in to the online channel. And Professor Goh and I have known each other for close to 20 years. It's a bit awkward to talk to him in a very formal way. So maybe I'll dispense with the formality and just address him by his first name. So Cho, thanks very much for joining us. Let me see if there are any questions that come in. Okay, so I guess we are still waiting to see if anyone have any questions. Maybe I will start with a question for you. Yeah. So I was wondering, Cho, in your opinion, do you think it would be more interesting for mathematics if the Riemann hypothesis, which you mentioned in your talk, is proven to be correct or is proven to be false? I mean, which one do you think excites you? Which scenario excites you more?
I always play some audio problem. I have too many sounds at the same time. I couldn't figure out what the question. Would you mind to?
Yes.
Hello,
okay,
by the way.
Yeah, so I guess the question I was asking was, you mentioned the Riemann hypothesis in your talk, and I was wondering, in your opinion, do you think it is more interesting for mathematics if the Riemann hypothesis was proven to be true or proven to be false?
My personal opinion, of course, is going to be true. I mean, I fully believe it should be true. I mean, it would be disaster if it is turned out to be false.
Yeah, okay.
Do you think so, we take?
Yeah, okay. Thank you. I think we have a question coming in from Ronwawin Chumpu. Sorry if I didn't pronounce your name correctly. So the question says, from the image of the Riemann zeta function, could we use the function to simulate phenomena like the Tonga eruption expansion, tsunami wave, or bombs effect?
Yeah, it would be very interesting thought. I'm not sure that I'm not sure you should do it, but obviously it does some point of zero with the function. Looks a bit like a lot of explosion of the, but frankly I do not know. I do not know if the function could be used to simulate a natural disaster. I think it's already busy enough to keep an eye or to doesn't need the mystery of prime numbers. It's probably good enough for the Riemann function to doing just that.
Okay, thank you. If there are other questions, please just send them in to the online channel. And in the meantime, maybe Cho, I can maybe I can ask another question while we wait for the questions to come in. So I wonder, in your opinion, how close are we to realizing, the expectations of the Langlands program? Do you think it is something we can achieve in the 21st century, or do you think it is, it goes even further in the future?
I mean, I'm pretty optimistic about Langlands program. I don't think that is something like it. I think it's clearly we have a lot of. I mean, we are making progress all the time, substantial progress, and we don't have clearly a strategy or a view on how to get the complete answer finally. But as you make constant making a progress. And yeah, I'm sure that it's going to keep us busy for a while, but it's not like Riemann. It's very different, like from the Riemann hypothesis, which basically make no progress in a lot from a very long time. So I remain very optimistic on the Langlands programs. I mean, maybe once we would solve on the question with Langlands pros, would be new question would pop up.
So in your opinion, you feel that the Langlands conjectures might be established first before the Riemann hypothesis?
Oh, definitely, I think so.
Yeah. Okay. Let me just take a look and see if there are some questions coming in. Okay, I don't see any new questions at this point. If you have any questions for Cho, can you send them through?
Yeah, but by the way, I would just want to add something that you only observe that I make a highly technical talk for GYSS. So that's the first time I have to try it. Usually I give much more elementary, down to earth talk on elementary mathematics. But I was asking myself why I should try to do something more radical. So I was trying to, at the same time to talk about history of mathematics, to introduce, to give you some kind of insight on what kind of mathematics you are doing. Professor Gan and myself are just very committed to this Langlands program that I present at the end of the lectures. Although most of you maybe you could have no notion of what I was talking about, but I just hopefully I give you some kind of feeling of about how what we are doing now is connected to the to the development of mathematics.
Yes, indeed, Châu. When you're, I have not looked at the recording of your plenary talk until just now, and I was actually amazed that you had the courage to introduce Adeles in your talk and to go all the way to the Langlands functoriality and reciprocity conjecture, and indeed, many of the names that you mentioned towards the end of your talk are people who are, living mathematicians today. So I think that it is good for young people to to see that this mathematics that you mentioned is not just a mathematics that live in the past, but it is something that normal people today, let's put it that way, are actually actively thinking about. So I think that this is a very sort of encouraging for young people to know that there are still lots of things to do in mathematics today. Okay, so I do not see other questions coming in at the moment. Maybe I'll ask a separate question, which is maybe just tangentially related to your talk, which is that maybe you could share with us what your research focus has been since since the fundamental lemma.
I have been changing a bit. I have been for a couple of years. I've been working on this Kosterman sheaf, for example. This is kind of one of the a beautiful object that I've been very curious since my PhD time, and then I did have a fun time to work on this with ZYU and Lucan Handlot, and then later I encouraged by Langlands, I will be trying to study functorialities and from many different perspectives. So that it become one of my main, occupations nowadays. Trying to realize this functional equation that I mentioned in my talks. It's very a lot up and down for a couple of years. I don't think I've made a lot of progress, but every time I feel encouraged, something new happens. So it's keep the hope alive somehow. And on the other direction, I was doing just completely different, unrelated. I was studying on the more like in complex geometries, question related to Hitchin vibrations. In my world fundamental lemma, Hitchin vibration come to merge with isomorphic forms through the fundamental lemma. But now I was studying both kind of different from the Hitchin vibration from more complex geometry perspective and functional equation by the more traditional automorphic method.
Yes. Thanks. So we have one question coming in. I think we maybe have time for just this one last question. This is from Samav Kapoor, and he asks, what do you think is a wise way to approach a really hard problem in math, like this conjecture?
Yeah, I keep saying that. There's it should be very wise in trying to approach a hard problem. You need to before starting working to invest your time. You need to have think that you do have some kind of chance to do it. Some very little chance, not big, but you need to have some chance. You need to have some kind of a beginning of new ideas or new approach, a new view of the problems. Otherwise, it's very difficult. Otherwise, if you keep trying to do what other people did, the chance is kind of very is not good, is not high. When I was when I spent a lot of time with the fundamental lemma, it took me in the whole it took me 10 years to do it, but for the very beginning, I think I got a chance. Even it was not big at the beginning. It just keep growing after that, because I had a kind of new method that people have not tried before. And if I have to do it by the other people who do it, I mean, there's no way that I'm smarter than other people. I mean, I need to have a new way to look at it if I have to have my chance. So that was that I always the advice that I keep saying to younger mathematicians before trying to very hard problem, you need to make sure that you have some kind of very little chance, maybe not big, but you need to be very sure that you have something new from the beginning.
Yeah. Thanks, Cho. I think actually there is still time to squeeze in one other question. So here's an interesting question from I think a Vietnamese student, Tron Ha Kwan. He asked if there is a connection between the Langlands program and fundamental physics.
Yes, I think there are elusive connection. I mean, from the very beginning, from the very mathematicians start working on infinite dimensional representation Lie groups before by the motivation from physics. The first people who work on this question are actually physicists. So the birth of the modern theory of automorphic representations has some connection with physics, and although it doesn't make appearance from now and then, you see automorphic form representation appearing on physics literatures, on the Einstein series, and so on. And for the kind of question that I was studying, fundamental lemmas, definitive physics play a big role, but the first people who actually introduced this modular space to mathematics, British mathematician Hitchin, he was studying some the Higgs bondons in some kind of simplified mathematic ways that give you this modular space Higgs bondons. It's clearly Higgs, the name is the same as the Higgs particles. Of course, by the end, it doesn't have much to do with Higgs particle, but the line of thought started from there, and also somehow you really have the feeling that it's not the same thing, but it's very much like there's some kind of very striking similarities that it's the same patterns that appear both in physics and in Langlands programs. And also this has been made more concrete somehow by Edward Witten when he gave some kind of physicsist solution to the geometric Langlands conjectures.
Thanks for sharing your thought, Cho. I think that we are out of time here, so I think it's time to bring this Q&A session to a close. Thanks for joining us again, and we hope that you'll be able to visit Singapore at some point in the near future.
Good morning, everyone, and thank you for joining us on day 3 of the Global Young Scientists Summit. My name is Jue. I'm the CEO of SG Innovate, and it is my privilege, a real privilege today, to be moderating today's panel, Startup Opportunities for Young Scientists. My work at SG Innovate is very closely related to this topic because at SG Innovate, our mandate is to work with scientists like yourselves who have entrepreneurial aspirations to build deep tech companies. And we do this by supporting them with early stage investments, by helping them to match them up with the talent that they require. And we connect them with partners and opportunities through community building. Now, deep tech as a moniker, I think, means different things to different people, but I think there is agreement that it's rooted in cutting, in some cases, bleeding edge research. And startups have a very important role to play in this because they are the ones who they are the transducers of this movement from technology in the lab to deployment in the marketplace. It is through this very arduous but immensely rewarding journey of translating research that we have to thank for many of the ubiquitous technologies that underpin modern life. In fact, many of the most promising emerging technologies, from mRNA vaccines to streaming to the handphones that we use, autonomous mobility, artificial intelligence, can trace their roots to the labs and research pioneered by our 3 very esteemed panelists today. This morning, we have the unique opportunity to meet the giants whose shoulders many of you will stand upon. And I think we've hit the mother lode here. We have, first of all, Professor Robert Langer. Professor Langer needs no introduction. He's a Millennium Technology Prize winner and one of 12 institute professors at the Massachusetts Institute of Technology. This is the highest possible honor awarded to faculty members at MIT. He is among the most frequently cited scientists of any field in the world and holds over 1,000 patents that have been licensed or sub-licensed to more than 400 companies. But Prof. Langer is also widely known for his own entrepreneurial streak. He has co-founded more than 40 companies, most notably Modular, in recent years. Next, we have Professor Alberto Sangiovanni-Vincentelli, currently the Edgar L. and Harold H. Butner Chair of Electrical Engineering and Computer Sciences at the University of California at Berkeley. Professor Vincentelli's expertise in electronic design led him to co-found 2 leading companies in the space, Synopsys and Cadence. Today, both companies have a market capitalization of about $100 billion. He enjoys working with businesses to understand where the innovation gaps lie and has advised some of the world's largest companies, including Intel, HP, General Motors, and Electronica. Finally, joining us in the Create building here in Singapore is Professor Stuart Parkin, who has come all the way from Germany. We are thrilled to get the chance to speak with Stuart in person. Professor Parkin wears 2 hats as the director at the Max Planck Institute of Microstructure Physics at Halle, and is also a Humboldt professor at the Martin Luther University of Halle-Wittenberg. He is no stranger to applying scientific research to the development of new technologies, having worked with IBM for several decades and was named as an IBM Fellow, the company's highest honor. Like Professor Langer, he was also awarded the Millennium Technology Prize in recognition of his pioneering work in spintronic materials, which have helped advance magnetic storage technologies. So I could go on all day, but it wouldn't be enough to do justice to the contributions to science and technologies that have emerged as a result of these breakthroughs. Over the next hour, we'll be hearing from them about their journey when they were young scientists and how they ventured into building and working alongside companies. I have 2 objectives. One is to address issues that you as young scientists may have as you contemplate your own futures, your own careers. And secondly, along the way, I hope to touch upon, that most vexing of questions, which is how do we make impact with research. And ultimately, that has to be done through commercialization, because that's what brings technologies into the marketplace and into our lives. Yeah. Throughout the panel, we'll also be looking forward to hearing your thoughts. And if you have any questions for our guests, I'm going to set aside the last 20 minutes for your questions. We're going to do this live, so we're going to patch you in live. So I'm going to need you to put your questions into the Q&A function, and look out for responses from Li-Ling of NRF in relation to your questions, because we can't go through all of your questions. We're going to select the ones with the highest votes, and we're going to select a representative question, and we'll patch that person in. So we look forward to seeing you in a short while. But for now, let's get started. To Bob and Alberto and Stuart, I'm just going to go in that order. I would like to get each of you to take us back in time and give us some insight into how your journey began. You know, as a young scientist at the start of your career, you know, what drove you? What was the imperative that shaped your decisions in research? Was it pure curiosity and the quest for knowledge, or was it impact and utility driven? That means, you know, you knew from day one, I wanted to increase data storage by 1,000-fold. I mean, did you know that right at the beginning, or what? And I'll start with Bob.
Sure. Well, thank you. I mean, basically, I didn't really have a clue. I mean, I was a chemical engineer. I majored in chemical engineering because in high school, my father and guidance counselor said, if you're good in math and science, that's what you should do. And my freshman year, the only course I was good in and I liked was chemistry. So I picked chemical engineering. And I went through undergraduate and then graduate school. And when I finished, pretty much all my colleagues, this was 1974, went into the oil industry, the petrochemical industry. And I thought I'd do the same thing. But what happened was, I'd go to these oil companies and I got offered 20 jobs, and I wasn't anything great, but they had so much money and so many openings. But they'd say, well, if you could just increase the yield of these petrochemicals by a tiny percentage, that would be worth billions of dollars. And I just remember flying home that night thinking to myself that I really didn't want to do it. And I just kept searching for trying to do something that I felt would help people. I did research and I was excited about research, but I wanted it to have some meaning. And I just struggled with finding something. I tried to look at teaching jobs and, because I was excited about educating students, but nobody would even write me back. So then somebody suggested to me that I should, so I started thinking about hospitals and medical schools, because again, I thought that's a way to help people through research, but none of them would write me back either. And then finally, one of the people in the lab suggested I write this surgeon in Boston named Judah Folkman. And I went to work with him as a postdoc, and nobody in chemical engineering did postdocs then. But anyway, I went to work with him, and I was the only engineer in the entire hospital. And it was just amazing. I got so many ideas from being there about how to use engineering and chemistry to address different problems and to make different discoveries. And so that's really how I got started. But it wasn't very well thought out on my part.
When you joined Judah Folkman, did you already have a research idea in mind, or you were taking the lead from Dr. Folkman?
It's interesting. I applied for a few faculty positions, and a couple of universities were, I should say, dumb enough to even offer me jobs, but my ideas were terrible. And he had this amazing idea that I thought that if you could stop blood vessels, that would be a way of stopping cancer. And I thought that was a fascinating thing. Nobody believed him, it turned out. People were very skeptical. And my job was to prove he was right. And in so doing, I developed the first blood vessel inhibitors. So I mostly took his lead, but I brought engineering into it because, we had a design to solve this problem. Bioassays. That actually involved me creating the first nano or microparticles that could deliver macromolecules like nucleic acids or proteins.
And that's where, okay, so he jump-started your career with an idea, and you kind of just let it flow. you went with the flow after that, with one idea after another, which you pursued.
Yes, that's true.
Yeah.
Not all would work, but yes, that's correct.
Okay. Thank you. I'm going to move on to Alberto. Alberto, can you tell us your story? When you were young, scientist, how did what drove you?
Well, actually, following the lead of Bob, I didn't have a clue either, right? So, but I started in my high school was classic studies. So I've done 8 years of Latin, 5 years of Greek, and all that kind of nice stuff. 5 years of philosophy, and then when I went to the university, if you were in Milano and you were a good student, there was no choice. You had to do engineering at the Politecnico di Milano. So there I went, and then.
But at this point, Alberto, can I just interrupt? You were
Yes.
doing classics and Greek. Why did you decide to go into a polytechnic?
Well, because as I said, it was the standard path for a brilliant student was to do engineering. It's similar to the French system, where engineering is the top career to take. I call Polytechnique, right? So anyway, and well, I didn't like it that much at all. And I ended up despising the practicality of engineering. So I tried to put some rigor in the thinking about design. But I was a theoretician, so I started working on as almost a numerical analyst. So I was doing solution of differential equation, large system equation. And then I got invited to go to Berkeley. So I went for 6 months as a visiting scientist, and 7 years later, I'm still there. And when I joined Berkeley, I started doing more theoretical stuff like nonlinear, non-differential optimization. But being in Silicon Valley, you start seeing things, and I was curious about all this industry and innovation and so on. And by the way, there were a number of people at what I was doing, and they said, well, it may be very useful to what we do. And then I went to IBM, H.I. Watson Research Center in 1980, and I got to work with the designers and IC designers, and I see a lot of problems that could be formulated in a good way, mathematical good way. And I did. And then in 1983, Intel came to my office, and they asked me, "Can you help us to design the 386?" And so I tried to help out, and it actually worked. And then we found Cadence, and then 4 years later, I founded an office together with a friend and a colleague, Richard Newton, and off we went. And so the interesting thing is that I didn't want to form any industry. So people say, well, gee, you are one of the quote unquote best entrepreneur. You had $100 billion company. Yeah, but it's just luck, right? Luck on one side, and the capability of jumping on a train that goes by. Right? And so I tell everybody, don't force it. So don't say, I want to do a company no matter what. It counts. It counts. If you have good ideas, it will come to you.
Thank you. Thanks, Alberto. Let's turn now to Stuart. So Stuart, unlike Bob and Alberto, did not end up as an academic. But tell us about it, Stuart.
Okay, so my case is I was always very interested in the natural sciences, and I always wanted to go up to Cambridge. I went to Cambridge to Trinity College, where Isaac Newton had been, and initially at Cambridge you can study a variety of sciences: chemistry, crystalline solids, mathematics. And after a year, my tutor said to me, "Well, physics is more fundamental than all the others. You should study physics." And that's what I focused on, because with physics, it's a language that enables you to describe the world as we know it. And it turns out that then I was very good at taking exams. I was always top in all my exams. And eventually, then I was offered a PhD position, and I decided to switch from theory to experiment for some unknown reason. And I became an experimentalist. I did my PhD.
But again, at this point, when you decided to switch to experimental physics, I mean, was there a trigger? Was there, you know, or you just said, sounds interesting, I'll just try?
I think I just felt that theory was maybe too abstract.
Okay.
And I think I was, even at that time, very interested in materials and how atoms order to create materials that have unique properties. So that's what I did in my PhD. Then I actually went to Paris for a couple of years to work on, again, it was really sort of automatic. It wasn't really, I specifically chose to go to Paris. I went there because it was a possibility, and I worked on organic superconductors. And that's why I ended up going to California, because I simply wrote to, they had a group there, 30 people working on organic metals.
Yeah.
There was a prediction they should become superconducting at high temperatures. Turns out, not yet today. And that's why I went to California. And then it turns out that at that time, IBM was a great place to work, because they were a very rich company, and they invested heavily in exploratory research, even research not much connected to the business of the corporation.
Yeah.
And so one could really do a lot of interesting things. And then after a couple of years, they decided to abandon this effort in organic metals. But the Almaden Research Center, at the time, it was the San Jose Research Center, they had 10,000 people 2 or 3 miles away working on magnetic disk drives. And they had no fundamental research program in magnetism. So they said, we're lacking fundamental program. Please start one. And so then I was charged with deciding what to do. So then I said, I want to go to this international conference for magnetism in Kyoto to find out what's interesting. And when I came back, I wrote a little report saying, the most interesting thing are these magnetic multilayers. And so then IBM gave me a lot of money to set up a lab. And I bought this fantastic molecular beam epitaxy machine. And then the manager said, well, Stuart, you're not an expert. We're going to hire an expert to run this machine. Go and do something else. So basically with 10% of the cost, I built my own little sputtering system. And it turns out designed for making atomically engineered multilayers. And with that machine, I could explore very widely, whereas this molecular beam epitaxy was so difficult and very exotic, very difficult to explore materials. So this tiny machine I built, I was able to explore hundreds, all by myself, with one technician helping me.
Incredible.
And so this is what I did. It was a lot of fun.
So at no point did you consider starting a company of your own? You were so well taken care of, you were so happy at IBM that at that point in time, there was no trick.
I think at that time, I was really interested in just working in the laboratory, doing experiments, exploring materials, having ideas. It was a lot of fun. And it was more fun than I think just to start up a company. But I think that, of course, it's very interesting to think about starting companies. But I'm more interested in the more fundamental exploratory research that then can be taken. Might take 10 years. So in my field, typically, it takes many years to take an idea, a new material principle into reality, maybe 10, 20 years.
Thank you. That last point is something I want to bring to Bob, because Bob, you've worked on some very difficult stuff. I mean, the stuff you did at Modular, I mean, it's at least a decade. And you know what Stuart was talking about when it comes to hardware, deep tech, let's say. I mean, it always takes time. In your case, I mean, you virtually industrialized, spinning off this whole process of spinning off companies. Did you find that there was a better way to bring ideas to the market? And importantly for our audience, what was the role of your graduate students in this process?
Yeah, well, as I was listening to Stuart, I was thinking for medicine, 10 to 20 years, in my opinion, would be fast. So yes, I'm envious. But, and in fact, like I was saying before, the work we started in the mid 70s on delivering nucleic acids, I mean, it really didn't come to fruition until, I think 1918, I'm 2018, well over 40 years later. It just always takes, medicine's very slow. But the story I was going to tell you is like again, a lot of this goes to my naivete, but also my desire at the same time to try to do research that I hope would do good. So, we published, I think, in Nature and Science in 1976 a couple of papers on drug delivery systems, and I thought very naively that if I did that, then not only would people cite them, but people would use them and make products. And I found that wasn't true. But about 10 years later, I'd get these calls from some very large multi-billion-dollar companies in the medical area, and then they said they wanted me to be a consultant. And I mentioned to them we had these patents, and they gave me grant and consulting fee. And most exciting to me, they were going to develop them. But what would happen with these multi-billion-dollar companies is they'd work on it for a few months, and it didn't work out exactly the way they wanted it to, so they just gave up. So one of my friends said to me, Bob, he said, we should start our own company. So we started a tiny company. And in fact, to the point that you made, the first 4 employees of this company were my students, either current or former, who worked on these micro and particles. And so we've done that repeatedly. I mean, but that's kind of how I got started. This little company, in contrast to the giant companies, well, they would live or die based on this technology, and they wouldn't give up. And of course, the students who'd worked on this, really believed in it, because they'd spent many years of their life in the lab working on it. So they'd try much harder. If something didn't work the first or even 10th time, they'd keep trying to get it to work. They did. So I think they played a huge role, and so that worked out well. Many products came out of it. Those were more microspheres that could release different drugs to treat diseases like schizophrenia or cancer, or even opioid addiction. But what I could see is that was exciting. And then, we just kept doing it. Like some of my students saw that I did it, so they wanted to do it. And some of the students over the years have become CEOs of a number of times have become CEOs or CSOs of the companies. And so they played an enormous role. And quite a few. I probably have 400 students who are professors, including
that's a lot.
And they start companies, including in Singapore.
Yeah, indeed. The last time we spoke, you mentioned a back of the envelope sort of distribution. What % of your PhDs have ended up in startups? Can you share that with the audience?
I would say it's probably about 40% in startups. I mean, some are in big companies, and we've many people have become professors all over the world. But I would say probably 30 to 40% are in startups, and they've loved
Incredible. Incredible. That's such a huge number.
But startups, of course, don't stay startups. I mean, they start out as startups. Like Moderna, we now have like 2,700 people, and some of the other companies have several thousand people. I mean, they could stay small, but usually the goal is to do more and more.
Well,
Alberto, you touched on cadence and synopsis earlier. Can you just share with the audience, in greater detail how all that happened, how you ended up co-founding these companies?
Well, in the first case, yes, Cadence is the first company that we founded, and that was directly out of the research lab. And as I said,
with graduate students?
With some graduate students, but mostly, I wrote with Richard Newton a business plan of the company, and we were the guys who the companies pushed to form the company. So this is a strange thing that it was not our idea to form a company. It was the idea of the people who ended up using the technology to push for forming a company.
I see.
And so it was a pull from the users that made us do the first step. It was the Cadence story. And then the second story was Synopsis, and that was, again, it takes about 7 years in our case to get a technology to be usable and to make an inroad in big companies, because we are B2B, so we do business with companies that produce things. And right now, cadence and synopsis, the two of them cover about 80% of the EDA market. And essentially, our research founded this field. And there is not a single company in electronic system design, including integrated circuit, that is not using at least one product from these two companies. But it all originated from research and curiosity-driven research, if you like. So trying to solve problems that were very difficult to solve. And,
besides cadence and synopsis, did you start other companies with graduate students and?
Yes. So well, I was also, never interested in leaving university, so I stayed a professor, and so that's the reason why I like to use new ideas and to see whether we can help big companies, but also form new companies. So some of the companies we formed was, for example, we unfortunately had to go in the big round of financing just on September 11th. So we had to pull back, and we eventually sold the company. That was a company that was doing among the first companies to do wireless integrated wireless communication. And then lately I've been involved with cybersecurity. So we founded a company in Italy that started very small, and we ended up going public, 10 million evaluation. Now is about 100 million. So after 2 years, so can't complain there, actually. And it's now trending to 200 million. So that's
incredible.
Nice. But again, I like to help out, and I also in following young companies coming from other neck of the wood, like for example in UK, I'm chairman of the board of 2 startups, one in quantum computing, another one in photonics. And just the way in which I try to help is to push on being rigorous about what they do, and to not to cut corners, and to make sure that what they do is solid and valuable. So anyway.
Thank you. Stuart, let me just come back to your experience at IBM, because sometimes the inner workings of these big corporations are huge mystery. And I think the audience might be interested to know. When you discovered sputtering, this whole process that you made high density, memory, and its ability to be mass manufactured. At what point did you realize, that hey, this is actually a product, or or did someone say, hey, Stuart, stop! What you're doing is, we can turn this into a product.
I think in my case, at IBM at that time, they were investing in a wide range of science and technologies. Of course, they wanted to invest in ideas that could impact the corporation. And it was a very large corporation with a very wide-ranging business. In my own case, then, I think because I work for IBM, then you had, if you came across something scientifically, because you had some idea of their technologies, then you knew there was some problem that needed to be solved.
Okay.
So in my case, let's say, when I worked on this, it was a very fundamental scientific problem I worked on. It was discovered that certain types of magnetic multilayers had interesting properties. And then I knew, that could potentially impact a magnetic disk drive.
Okay.
For example, to build this reading device. And that was a limitation at that time in the performance of disk drives. So in that sense, working for that corporation, I knew about these problems that needed to be solved. I think that was what made it interesting. Sometimes in academia, if you're just a pure academic, then even if you do exciting research, you don't really have the problem. You don't have a problem to be solved. And moreover, often, I think in academia, you think, I've discovered this interesting property. But typically in technologies, you don't need one property, but that particular material or device have a whole range of properties to be useful. And having an exquisite property in one dimension doesn't mean it will be useful unless it can also survive temperature, be manufactured, all sorts of other things. And I think academics
these are the
don't appreciate that.
properties. presumably in a big company, the advantage is there will be people who will be able to tell you what else is needed to make this manufacturable, and how to and what the trade-offs are, what trade-offs are required in your technology in order for it to be
I
mass
think
produced.
in that sense, it's similar to an academic world. There are experts in all these different disciplines. And of course, you can approach them to ask them questions if you have a question. I think in that sense, in academia, also if you're in a large university, there's always somebody, if you have some idea and you want to answer a question, it's very nice because you have people you can communicate with. This idea of collaboration, interdisciplinarity is very important, I think.
And so once you solve the problem, so to speak, what happens? You hand it over to somebody else in the big company to
in
to
my
make,
case,
or
what was very interesting was I had my own ideas about these materials, and there was another group working in IBM, much larger, closer to the technology, and they didn't believe me. And they said, "Oh, it's not what Stuart says; it's this other thing," and they were totally wrong. And then the fundamental science, I thought I knew what was going on. And this other group that actually represented 90% of the academic community, they had this other approach. And I thought they were totally wrong. It turns out I was totally right. It turns out the interfaces totally dominated the properties of the materials, making them super interesting scientifically and technologically, because you could manipulate these interfaces on the atomic scale and create new properties that were not otherwise there.
But this experience, of course, leads me to a question which I'm sure many have in their heads. There's this thin line between madness and genius. Very often VCs will say, "Fail early, fail fast," whatever it is. How do you decide that? I mean, this is a great example. I mean, 90% of academia said that approach was the right one. I mean, how do you decide when to stick to your guns? And when do you decide, hey, maybe a bit of reality testing is in order?
I think somehow I feel that some people, some scientists, what is correct, and then you have to follow through on your beliefs. So in some sense, in that sense, a little bit surprising with scientists, so we're based on concrete evidence. But at the same time, it's your understanding, your appreciation. Somehow you have that insight that maybe somebody else does not have. And you have to really believe in that. Because as Bob said, okay, it may take 10, 20, 30 years. And if you don't fundamentally believe in this concept, then you won't work on it sufficiently
but this belief
to
is
prove
based on
that it
intuition,
works. I think a lot of it. Well, I think, I think science, in my own mind, what's exciting, we really want to understand how the world works. And we can write a language that can describe much of how the world works, but that's only partially. It's incomplete. It's like any language, you cannot describe completely. And I think somehow you can see between the words, if you like, and you can have that appreciation that maybe it's a little bit of intuition, I feel is very important. And if you don't really believe in something, you won't have that perseverance to work on it. So in my case, the very fact that these other people are saying, "Oh, you're totally wrong," meant I had to do more experiments to prove that I was right. And by so doing, I would make more discoveries and make my ideas even more valuable to IBM at that time, but could change the world. And I think that was very interesting.
Bob, would you share that sentiment? I mean, I read your Forbes interview. I mean, you faced a lot of challenges in your early days, but you just kind of, you soldiered on and you won. And in those moments where things weren't looking so positive, what drove you to? I mean, how do you know when to stick to your guns and when to fail fast?
Well, I should make a comment about failing fast. I think it's over, I certainly understand the idea of doing critical experiments, and I certainly agree with that. But when I look back at what I've been involved in scientifically, and I think this is probably true for the others on the panel and lots of other people, it's like you develop what I'll call a platform technology, meaning that you can use technology for many, many, many things. So I'll just pick this example going back to the 1970s. So we published a way that you could use micro or nanoparticles to deliver pretty much anything, any large molecule. And on the other hand, so to get it out to the public, obviously, we did, it takes a lot of money in medicine, takes a lot of money in anything, but we started companies. And I should say that the challenge to me, in my mind, and we had lots of failures, but the challenge to me in my mind was not necessarily a scientific failure where you could fail fast, but sometimes there's business failures, there's regulatory failures, FDA kind of failures. Sometimes you work with a partner company and they pull out. So what would happen is, and what I've observed is when you're trying to do the kind of work we do, that it's really a team effort. In other words, we may have provided the basic science for this platform, but usually you need good business people to partner with you to help figure out what is the right first application, second application, third application. Now, if it were up to me, I'd probably fail a lot because what do I know about marketing? And by the way, you can't predict these things, right? I mean, who would have predicted that nanoparticles would be useful for delivering messenger RNA for COVID vaccines in 1976 when we published the paper, and nobody would know. And so I think that, and I certainly, I mean, not even on the radar screen. So some of the applications we picked didn't do well, others did do well, but I don't think just because one failed. In other words, just as an aside, we had started a nanotechnology company, I think in 2006 to develop targeted nanoparticles, and the company didn't do well. It went, bankrupt for a period of time, ultimately got bought by Pfizer. But, when that happened, there were all these articles in Nature and CNE News and other places that talked about nanotechnology being a failure because of that. And my feeling was, well, that was just because of one target that we chose, but it wasn't true for the technology. So I think that you always want to get answers as fast as you can. I really believe in that. But if you have a platform technology like, a lot of us are doing, I don't think you will fail. I think that you just have to find the right application, keep soldiering on because you believe in that you've done this work and that it does work. You just have to find what the killer app is, so to speak. And if I can find it, maybe somebody else will.
Thank you. Okay, I'm seeing a lot of questions on the question board. So I am going to invite the first question from the audience. And the first question is from Hafiza Ishrat Fatima. And her question is to Bob. Hafiza, I see you on screen. Please go ahead. Please ask your question.
Thank you so much for giving me the opportunity. Actually, I want to ask the question from Robert Langer, that what driven you when you switch your field from chemical engineering to entirely a different biology field? And then that doesn't stop you, and you further discover the nanoparticles and also your contribution towards the biotechnology and regenerative medicine. So what did you do? How did you find the biology and manage to understand the biology from the very scratch?
Yeah. Well, if I understand the question, and there are a number of dimensions, so you can correct me when I don't answer all of them. But what I think you're asking is, how did I sort of learn the biology? It's a really good question because I didn't know biology at all. In fact, I still don't. The last time I took a biology course was in 10th grade. But, what I would do is I would, read papers, scientific papers, and I understood maybe about 10% of them in the biology. And then I'd go to the lab and I'd do something, worked on it for a week or so. And then I'd go back and read the papers again, and this time I maybe understood 20%. And then I'd keep going back and forth like that. And eventually, I between doing experiments and then reading the literature, I would understand it more and more. And I probably do that to this day. I'm lucky now, that I've got a lot of smart graduate students and postdocs, and they educate me. And I've got a lot of great collaborators, and so you keep getting educated. But it's not an easy thing when you don't know the area, so you just have to keep looking at it. But that's how I did it.
Yeah, that's actually my point. Like, because when you are done with your PhD, just you are more concentrated to that field, but you entirely change it. So that was the thing, that if we change the field, because we are the young students, and now the era is like multidisciplinary, and we should engage this thing. So I think that's the better tip and trick to do that, to do the experiment and then study it, and you can manage to.
Yeah, I think that I mean, for me, that was a good way to grow. You know, I was able to. I've probably spent my career combining engineering on the one hand, or materials on the one hand, with medicine and biology on the other. So it stretched me. So I think the interdisciplinary thing, at least for me, was very helpful.
But you know,
Thank you so
Hafiza,
much.
if you think, Hafiza, if you think that was difficult, imagine what Alberto did, moving from the classics to electronics.
Yeah,
Alberto,
that's
you want to
actually the
just
one.
chip in? I mean, very quickly, how did you do it? I mean, it's a
Well,
complete switch.
Yes, complete switch. But yes and no,
It's
because
like,
most of my things then later on my methodologies, actually I fished out of my philosophy and Greek background, believe it or not. But the notion of time in my methodology was actually taken out of St. Augustine, Kant, and so on. Right? And that was extremely important just to understand the essence of things. So, and in fact, the abstractions that we use to solve complex engineering problems come from this thought of how do you eliminate orthogonalized concerns. And then again, it's a platform technology, right? Once you find the hammer, everything looks like a nail, right? So you go one after the other, right? So I started integrated circuit, then did automotive, then did airplanes, then I'm doing buildings. So same story, same platform all over again.
Thank you.
thank you
Hafiza,
so
I'm
much.
going to move on to the next question, if you don't mind.
Yeah, thank
Okay,
you so
and
much.
thank you for joining us this morning. We're
Thank
now
you for
going to
having
move
me.
on to the next question, and this is a question from Diana Xiao.
Hi.
Diana, can you tell us where you're calling in from?
Yeah,
And then I think this is probably a question that maybe Stuart looks like he's best positioned to answer, especially in relation to the corporate setting. But please go ahead and ask your question, Diana, please.
Sure. Hi, I'm Diana. I'm from Hong Kong. And so I really enjoyed your life stories, I guess, but I wonder with the way research funding has changed in both the academic and corporate setting, whether or not you think your career paths that each of you experienced is still possible today.
Stuart, you want to take a crack at it?
Sure. Yeah. I would say it's totally possible. I would say today the scientific arena is much bigger. The numbers of companies that you could work for are much bigger. There's somehow more money available, I would say, to do research. I mean, maybe IBM itself as a company is not perhaps as successful as it once was, but that's the nature of things. Companies evolve over time because they tend to stick with what they know, and then new things come along and they're basically superseded. You know, the lifetime of typical companies is only 10 to 20 years. There are very few companies, IBM is actually more than 100 years old, but there are very few companies that survive more than 1 or 2 decades because of the evolution. Technology continues to evolve rapidly, as does our scientific understanding. So I think though today, there's lots of, if you wanted a corporate setting to do for your career, there's companies with huge amounts of money like Google and Microsoft, Facebook, who are changing the world even as we speak. On the other hand, the academic path is still viable. And I think this concept of interdisciplinary science is super important and not just sticking to one field. And I think today that is what is different, because with knowledge, it's accessible to everybody in the cloud, on the internet. So basically, you don't need to be as specialized as once one needed perhaps to be. You can know more about many fields by that information is totally available to you, I think. So it's easier in some sense today maybe than it was 30 or 40 years ago to have new ideas and to make them happen, have impact.
So you think it's a misconception that maybe the funding is more directed to immediately successful kind of ventures or more already successful people?
I think that is a misconception. I think what happens is the amount of funding in the exploratory science, pure exploratory world is larger than it once was. But what one sees it's a tiny fraction of all the investment that is going on in startup companies, in big companies, because it takes so much money to have impact today, I think. So I would say but that arena of exploratory science still exists. There's fantastic exploratory science. Let's say gravity waves were discovered, took 30 years to build the instrumentation to do that, but that was pure science. So pure science still exists. People want to address those questions of the world that we would all like to know the answers to in astronomy, in astrophysics, in nuclear physics. I think that still exists. And at the same time, exploratory science in the terms of how can we accelerate our ability to expand those frontiers of our knowledge. I think this is a very interesting question. And I think is being helped by all sorts of developments in artificial intelligence, machine learning, all sorts of things. So the speed of development, I think, is, if anything, is increasing. So you can have an impact, but maybe your impact will be faster than it once was. And then you have to do something else. In that sense, it's super exciting today, I think. Even more exciting than it was when I started a long time ago.
Thank you, Diana. I'm going to move on to the next question, but thank you for joining us this morning. Yeah. Okay, next we have Lex Van Loon calling in from Australia. Lex, all yours, Lex.
Thanks. My name is Lex. I'm calling from Canberra, Australia, indeed. And I have a sort of a corny question, but hopefully we can learn something from it. Because from my own experience, failures tend to learn you the most. So my question is a simple one: is what is your biggest mistake, and what did you learn from it?
Alberto, you want to go first, Alberto?
Yeah, well, it's interesting because in my case, actually, failure did not happen in a dramatic way, and was maybe in misjudging some people that I thought were very good and were not, and some people I thought were, were not so great, and then it turned out very good people. So, and in particular, when it comes to funding companies and then helping companies to grow, sometimes you pick the wrong person to do an essential job, right? And then you have to correct it. And that is painful because it may jeopardize the life of the company. So my mistakes were mostly in that domain. In terms of the technology, I may have been very lucky, but I don't think I had any visible failure at something. Maybe I failed in judging how long it would take to have a particular methodology being picked up by industry, but in the end it happens. So it's the timing that I missed.
Bob?
Yeah, I'm trying to think which is the best failure. But I'll pick one that I think may fit what you're saying. So when I was in 8th grade, I'll go back a long ways. They made you give talks. Like I had to give a 1.5-minute talk. So, and I was very nervous. I practiced that talk for 3 hours the night before in front of my parents' mirror, and I kept rehearsing it. And the next day I got up in front of my 8th grade class and I did the same thing. I didn't have the paper in front of me though. So for the first minute, I actually did okay. I was probably like a zombie just reciting this thing. And then I just couldn't remember the next word. So I stood up there in front of my 8th grade class for another minute, just saying nothing. And finally the 8th grade teacher told me to sit down and gave me a failing grade of an F. And it was humiliating, but it really made me realize that, being able to do public speaking was important. And of course, for a long time, I tried to avoid it. But, as I got older, and certainly when you do science, you give talks. And I made a point of watching people give talks and to see what they did that I liked and what they did that they didn't like. So eventually, I learned to be an okay public speaker. But I just really made a point of it because I was just so bad early on.
Great advice. Great advice. Stuart?
I think that was fantastic advice from Bob. But I would say, if I look back, I think I should have taken more risks. And I think that's, if I would say anything, I should have, believed more in what I thought and taken more risks. I think I would think that's what one should do.
Well, it's not too late, Stuart.
No, yeah, not too late. Thank you.
All right. Thank you, Lex. I'm going to move on to the next question. And for the next question, we have Rosa Guerra Resendez from Texas in the US. Rosa, can we patch you in?
Oh no.
Okay, just give it a second. No, okay, it's not. It looks like it. That's not happening. Let's move on to the next question. And her name is Anissa Fitri Rayu, calling in from Japan. Anissa?
Oh.
Just bear with us.
Anissa.
There we go.
Hi.
Hi, Anissa.
Hi. Thank you for the opportunity. Because all of you are great scientists also and running a company, so I would like to know, how do you manage conducting research for publication in terms of contributing the development of science and also commercialization for your company? And could you give me the proportion of your research in two different purposes? So like strategy for your researcher also if they want to build a company. Thank you.
I don't know, Bob. You wanna start first?
Sure.
How do you allocate your time and your bandwidth to doing two things?
Yeah. Well, basically, to me, the way we do it at MIT, or the way I've tried to do it in the lab, is one is a natural extension of the other. You know, you do basic research in the lab, and you try to solve or understand things or make inventions that you feel are important. But it's pretty basic science or engineering research, and then you write a paper. But what I've also learned is you might as well try to write a patent at the same time. You could almost use that paper as the basis for a patent. And that patent, you know, could be a basis for starting a company. And in particular, this goes back to one of the earlier questions. If some of the students who worked on it want to start a company, and we feel it's far enough along in terms of proof of principle and you know, and so forth, and often we do, you know, start a company. Some of the students work at the company. We raise some money, and I'd say that the company does more development. They may do some research. Development meaning, you know,
Thank you, Anissa. I'm going to go back and take the question from Rosa, who I understand. So thank you very much, Anissa. We're now going to patch in Rosa. Hi, Rosa.
Hi, everyone. Sorry, my computer was acting up. Thank you so much to all the panelists for their very insightful experience and comments. My question is more about starting the startup itself. Like most startups fail to become big companies. So what would be your advice to young entrepreneur scientists whose first attempts as startups might fail initially?
Oh.
Alberto, you want to take this on first?
Yeah, well, I mean, in general, when you start a company, you should always pose the bar very high. So you don't form a company just to survive. You want to form a company to change the world and to impact the field in which you work. And so every time I see, you know, I dab also as a bit as a venture capitalist. So I hear young people to present ideas, and I always ask them, so what is your exit strategy? What do you think your company is going to do at the end of the journey? Do you want to be number one in your field, or you want just to stay average? If you want to stay average, maybe you shouldn't form a company. So in general, a good way to fail is just to be ambitious and then too bad it didn't happen, right? And so you try again. But if you don't have that kind of drive to change the world, to do something important, then once you have a failure, then try again. But if you see that failure as a step towards making a big impact, then it's okay. So my advice will be, if you fail, reassess your mistakes and see where something went wrong, but always strive to make it big.
I think, Bob, you've got a lot of experience here. You wanna chime in?
Well, the first thing I was going to say is failure is okay. That's really important to realize. You know, I think one of the things that's been so good, at least to me in the United States culture, is that, you know, people fail and it's accepted. You know, Bill Gates has failed, Steve Jobs has failed. I mean, I'm sure all of us, probably, at least me, I've certainly failed. So I think that's the first thing. I think the second thing, though, is I think it's really a good idea to have partners. You know, like for me, I'm a scientist, but I've had good business partners. You know, if I work with a really good chief executive officer, you know, business people, that makes a big difference. I've often said that the companies I've been involved with that are most successful, as much as I'd like to just wish it were the science, it's also, if not more important, to have great business people. And tied to that, finally, especially if you're doing something that's really expensive like medicine, is to have really good patient investors who understand that you're not going to solve problems overnight. So I think you can mitigate risk by some of those things.
Thank you, Bob. And on that note, I think I'm going to need to bring this to a close because we've reached our hour. Rosa, thank you so much for dialing in today, all the way from the US. Thank you. And to all our panelists, once again, Bob, Alberto, and Stuart, thank you so much for doing this with us this morning.
Well, thank you.
Thank you.
Yeah.
Thank you.
Have a good night.
Thank you again.
Thank you.
Thank you.
Okay.
Ladies and gentlemen, welcome to the Global Young Scientists Summit 2022. Today, I have great pleasure to introduce to you Professor Barry Marshall, Nobel Laureate 2005. Professor James Barry Marshall is clinical professor and branded ambassador at the University of Western Australia. Professor Marshall and Emeritus Professor Robin Warren were awarded the 2005 Nobel Prize for Physiology or Medicine for their discovery of the bacterium Helicobacter pylori and its role in gastritis and peptic ulcer disease. Professor Marshall was at the Health Science Center at the University of Virginia for 10 years before returning to Perth, Western Australia, to his post as clinical professor of medicine at the University of Western Australia. Today, Professor Marshall is director of the Marshall Center for Infectious Disease Research and Training. This center is obviously founded in his name. And in addition to Helicobacter pylori research, the Marshall Center is also at the forefront of infectious disease identification, surveillance, diagnostics, and drug design, and transformative discoveries. His research has expanded with his group to embrace new technology including next generation sequencing and genomic analysis. As a personal friend of Professor Marshall, I know that he is a very nice person and also very innovative person. You will hear from him his amazing story of how he was driven by curiosity to discover this bacterium in the stomach, which was supposed to be unbelievable. And I'm sure you will enjoy his story, how he will be led to the path of getting the Nobel Prize. So today, his plenary topic is how curiosity-driven research resulted in the Nobel Prize in medicine. I give you Professor Barry James Marshall.
Hi there. I'm Barry Marshall. I'm Clinical Professor of Microbiology at the University of Western Australia in Perth. And it's my pleasure today to give you a lecture for the Singapore Global Young Scientists Forum. The title of my talk, as you see, is How Curiosity-Driven Research Resulted in the Nobel Prize in Medicine in 2005. So as you know, this discovery was related to the stomach bacteria Helicobacter pylori, and you'll learn more about that as we go through the lecture. Now, it's extremely common. I'm not going to talk about the epidemiology of it very much today, but we found out ultimately that about half the people in the world have this bacteria in their stomach, and it can lead to ulcers and, worryingly, stomach cancer. So we'll start off way back in 1979 when my colleague Dr. Warren, who's a pathologist, had his first case, and I think it was his 42nd birthday. He's still got the records of that pathology report that he did. So this is what he saw. Now, initially, when you look at a biopsy, it's usually a H&E section, and so the tissue is pinkish, and the bacteria, if they are there at all, might just be very faint bluish smudges. So Warren saw these bluish things on the surface of the biopsy, and he wanted to have a clearer look, so he asked for a special stain called a silver stain, which stains the bacteria black and the tissues a golden color. And here you see his first case. Now the thing you'll see there is that you've got yellow cells, and these are the cells that line the stomach. The clear area is the mucus layer, and the black things there all over the place, especially on the surface of these epithelial cells in the stomach, are the bacteria. And we now know that they are Helicobacter pylori, but in those days when we first named them, we called them Campylobacter. So Campylobacter means curved bacteria, and Helicobacter means a bit more, it's spiral, like a corkscrew. And Helicobacter pylori, the name we gave them in the end, means that a curved bacteria or a spiral bacteria living at the bottom end of the stomach near the pylorus. And pylorus is the Greek word for gatekeeper. And so that reflects the function of the pyloric muscle at the bottom end of the stomach. So that's how it got its name, and now we will just call it H. pylori, because Helicobacter is a pretty long name. So here's Dr. Warren's first slide, and you can see that all the curved bacteria stuck all over the surface of the epithelial cells, and they are black. And that magnification there is about 1,000 times. Now that's one of the reasons these bacteria had not been discovered before. They had been discovered a few times, but most pathologists didn't see them, because most pathologists will diagnose cancer, stomach conditions, etc. at a low power, say 250 times, and at that power you cannot see the bacteria. So here's the curiosity-driven research thing. Bacteria are killed by acid if the pH is less than 3. So that's like strong lemon juice would be 3. Stomach has acid in it, which is pH of 1.5. So about 10 times or 20 times more acidic than the strongest lemon juice you can think of. So the question is, how can bacteria live in the stomach when there's acid everywhere? So that's why nobody ever looked for bacteria in the stomach, because common sense would dictate, oh, they can't live there because we know bacteria are killed by acid. So we wondered that. How can they live in the stomach if there's acid there? And we started this collaboration, and I started with Dr. Warren in 1981, and we worked pretty intensively on this project for about 5 years after that. And here we are after our first publication in The Lancet. And you know, The Lancet is one of the most widely read medical journals for clinical medicine in the world. And that was our first paper, really, or my first paper at least. And here I am in Dr. Warren's lab, and we're looking through his pathology books, noticing things about gastritis, stomach cancer, bacteria, etc. Warren and I did a study of 100 patients coming to have an endoscopy, which is the tube down the throat, look in the stomach for cancer or ulcers, etc. And so the fibre optic endoscope went down, and biopsies were taken for microbiology and pathology, and all the data was collected. And I studied it a few months later, and this is what I found. So in the bottom line, you see the total of 100 patients was that 58% had the bacteria in the stomach. So they were surprisingly common. However, when people had a duodenal ulcer, which is the most dangerous and most common form of a peptic ulcer, because you can bleed to death from a duodenal ulcer, you'll see that of 13 patients, all 13 or 100% had the bacteria. So that was highly significant. P-value is 0.00044. So it's like throwing heads 13 times in a row, or red 13 times in a row at the casino. And also gastric ulcers, which are ulcers in the stomach, 22 patients, 18 or 77% had the bacteria. So again, highly significant. So we're pretty excited about that, and we wanted to follow it up and publish it. And this publication was in 1984. By that time, we had already been testing patients for nearly 3 years. So we were starting to understand that this was a consistent finding, and wherever we looked, we could find this association between the bacteria and ulcers. However, I ask you, would the world accept the new cause for ulcers on the basis of data from only 13 patients? No way, because it was an important discovery, and too important to suddenly change the paradigm. And you know, the current paradigm at that time was that ulcers were caused by stress. And there were plenty of people that were making a living treating stress in ulcer patients. And now we know that stress has got absolutely nothing to do with ulcers. So no way. No one's going to believe it straight off. They want further evidence. And Warren and I tried to present this at the gastroenterology meeting in 1983. And we received a letter back from that conference planner. Dr. Marshall, I regret your research paper was not accepted for presentation. The number of abstracts we received continues to increase. And for this meeting, 67 were submitted. We could only accept 56. And so ours was in the bottom 20%. In fact, it was one of the worst ones as far as the judges were concerned. And they said, Dr. Marshall, I'm sorry, you haven't been selected to present your paper. Not only that, we're not even going to let you present a poster. It's a bit too strange, and we would be quite happy if you don't come to the conference, because it's a bit shameful to produce research like this. However, Warren and I were very confident that there was something going on, because we knew of previous discoveries of these bacteria in the stomach going back 100 years. And they had already been discovered, and recently I published a book called Helicobacter Pioneers, and you can see the table of contents here: 1892, 1917, 1940, 1950, 1957, 66, 73, 75, 78, 79, 73, 79, and 82 was Warren and Marshall. So about 10 other people had published done a thesis on bacteria in the stomach. Not always human, but sometimes dog stomach, mouse stomach, etc. So one of the most important one was this guy, Stone Friedberg, and he later became a famous professor at Harvard, and he was a cardiologist, I believe. But when he was a young man, he discovered that spiral bacteria lived in the stomach, and he had quite a few patients, and at post-mortem or at surgery of the stomach, they had samples showing that bacteria were present. This is him when I met him a few years later in Boston, and finally this is when he was about 100 years old at Harvard Medical School. He's looking through his thesis there. So he discovered spirochetes in the human gastric mucosa and published it. And this is one of his pictures, a black and white illustration. But as you can see, the wiggly bacteria there inside a gastric gland look very similar to those ones that Warren and I were seeing in 1982. However, nobody believed it because the top pathologist in the United States, Eddie Palmer at Walter Reed Hospital, he found that Friedberg and Barron were proven to be wrong, but unfortunately he had incompetent researchers working for him, and nobody knows how he missed it. But he said none of the 1,180 specimens was found to contain spirochetes or any structure which could reasonably be considered to be of a spirochetal nature. So he published this, said, we looked at 1,000 cases and we didn't see any. So Friedberg's things must have just happened after you died or after they cut the stomach out. Other bacteria grew there. Nobody bothered about it. It was just useless information. And I'm sure Dr. Friedberg was a bit disappointed by that. Now, in the 60s, one person took an interest in them, Susumu Ito. He was also at Harvard, and he had one of the best electron microscopes in the world then, and he was describing the anatomy of the stomach, and he was looking in cat's stomach, and he saw spiral bacteria in the stomach of the cat. And so one day he said, well, I wonder if humans have these bacteria in their stomach. So he swallowed a biopsy tube, which is on the end of like a long cable, and on the end of the cable is a little knife which cuts a little piece of tissue out of the stomach, takes it out and stains it. So he had very, very fresh tissue, and he was very good at staining for bacteria, etc. And he produced this photograph, which is Helicobacter pylori, and it's actually from his own stomach. And we now know that Helicobacter pylori is extremely common in Asia, especially in Japan, where nearly 100% of people used to be infected with Helicobacter. And you know that was the #1 country for stomach cancer in the world until about 10 years ago. So here it is, Helicobacter, and you'll see on the end you've got a couple of flagella sticking out there, and it's firmly attached to the epithelial cell with all kinds of lectins and things there, which are not particularly well understood, but it's very, very interesting. So that was published in the Handbook of Physiology, and there he is, Susumu Ito at Harvard Medical School, when he and I were corresponding in 1995. But the question is, when you discover a new germ, how do you prove that it's a harmful pathogen? And there are a few rules about how you go about it, and one of the key things that you try to do is infect animals with the bacteria and see if it can produce some similar disease in animals. So our experiments included mice, rats, rabbits, guinea pigs, pigs, and ultimately a human, which was me. So in preliminary studies, which were not well documented, we tried to infect the Helicobacter into mice, rats, rabbits, and guinea pigs, but no effect. So Helicobacter pylori is specially adapted for the human stomach, and it probably does not stick to animal stomachs very well. So therefore it can't cause the infection. And we tried to infect piglets, and I was feeding the bacteria to these piglets and doing endoscopies on them once a week to see if the bacteria had taken. But the pigs grew, and we found that after 6 months the endoscope was not long enough, because if you have studied pigs, you'll know they have a very, very long body, and so that the human endoscope wasn't adequate to do endoscopy on those animals. So the experiment failed. We could not infect pigs. So in 1984, a human volunteer was given H. pylori. Now, although it sounds pretty interesting to do an experiment on yourself, it's really not very scientific. And so I was always a bit embarrassed about telling people that I had drank the bacteria. So ultimately, the Abbott company, who made antibiotics against Helicobacter, you might have heard of it, clarithromycin was the best one. They produced a comic strip about my experiment where I drank the bacteria, and it was published in the Medical Journal of Australia actually in 1985, not 1984, an attempt to fulfill Koch's postulates for Campylobacter pyloridis, and that's the name we had for it in those days. And here I am, my lab tech says you're crazy, and I'm there. There's no other way. And there wasn't any other way because we had tried it in animals. So the details of the experiment are that I underwent a baseline endoscopy, and looking in my stomach was completely normal. All the biopsies were normal, no bacteria, lots of acid. So I drank bacteria, which was 10 to the 9th colony-forming units, and that's how you measure bacteria. So that was 2 Petri dishes covered in growing Helicobacter pylori. So after 3 to 5 days, I felt vaguely unwell, and my mother and my wife both told me that I had halitosis, a bad breath. So in retrospect, the low acid level was allowing all kinds of filthy bacteria to start growing in my stomach and causing halitosis. I think that's my explanation of it. Then after day 6 to 10, I was vomiting, and the vomit didn't have any acid in it. So finally on day 10, I had another endoscopy to see if the bacteria had taken, and what do you know? I had severe gastritis. The bacteria were all over the place, and that proved that Helicobacter pylori was a pathogen causing this inflammation of the stomach, which we call gastritis. But I did not develop an ulcer, and you can read about the details of that experiment on Wikipedia if you want to. So here's my silver stain. The stain is a bit brownish on this occasion, a slightly different one, but you can see lots of those beautiful bacteria sticking to the epithelial cells. And if you looked at other parts of this biopsy, you could see lots of white cells in the stomach trying to eat the bacteria, trying to eradicate the infection. And I had an infection and was a bit unwell then for about another week. So that experiment was published in the Medical Journal of Australia in 1985, and people around the world were pointed to it by an editorial in The Lancet and a bit curious about it and pretty interested. And one of the people that was interested was the microbiologist at Procter & Gamble in Cincinnati in the USA. Now, I know that Procter & Gamble is a global company with all kinds of well-known brands. So, for instance, soap powder, especially Tide and Bounty, different kinds of diapers, toothpaste, shampoo, you name it. But they also produced some gastric compounds for unsettled stomach, particularly in the United States, so that you would see why they were a bit interested in stomach treatments. And here I am at the University of Virginia in 1987, probably. So here's that medicine produced by Procter & Gamble at the time, and that's called Pepto-Bismol, and had been used to treat people with gastritis or gastroenteritis, any kind of gastric upset, for about 100 years. But in its original formulation, 100 years before, it said in conjunction with other indicated remedies, it's been found of service in treating gastric ulcers as well as the relief of acute gastritis. So it had a bit of a history of being good for gastritis, even though there was not really good scientific data about this. So I had mentioned this in one of my papers, and that's what pricked up the ears of Procter & Gamble. So bismuth, a close relative of arsenic, and arsenic was another thing that was used in small doses for all kinds of GI complaints before the era of antibiotics. And so it remains as a modern equivalent of Kobayashi's arsaminol. So Kobayashi was the guy in Japan studying stomach bacteria, and he was treating them in mice with an arsenic compound called arsaminol, which was also used to treat syphilis. The popular medicine Pepto-Bismol in the USA has been shown to kill Helicobacter and heal ulcers. So that was shown subsequently. And so Procter & Gamble, as you can imagine, were pretty excited because there were billions of dollars to be made by discovering new ulcer treatments. And that research goes on today. So here's an experiment I did in 1983, actually. And here you see a culture plate showing Helicobacter pylori. And in the middle, I've got a disc there, which has got some Pepto-Bismol, or bismuth subsalicylate is the chemical name of it. And you'll see a very sharp zone of demarcation, how the bismuth is toxic to the bacteria and they can't grow anywhere near the bismuth. And this is a picture of a biopsy, and this person took some Pepto-Bismol and 30 minutes later had an endoscopy and some biopsies. And the interesting thing is that these black metallic spots have precipitated all around the bacteria, so the bismuth gets concentrated by the bacteria and then kills them, and they detach from the mucosal cells. So really quick and really effective treatment, and maybe that's why it was so popular for stomach upsets for 100 years. Even today, people are talking about H. pylori and how you kill it. So usually you take an acid blocker and some antibiotics. And here's a drug company. This is AstraZeneca's mouse pad, which I'm actually using here today. So low-sec HP7 shown here was the first really good treatment for Helicobacter, and that consisted of omeprazole, an acid blocker, and 2 antibiotics, which is amoxicillin and clarithromycin. So several drug companies teamed up to produce this medicine, and people have been taking it all over the world for 20 years. It's still one of the best. But in there, they were a bit worried that there was a lot of competition from bismuth, but Procter & Gamble treatment. And so they like to say no bismuth because some people reckon that bismuth was dangerous to take. It's not true. It's never ever caused any trouble. Even after 100 years, I've hardly ever heard of side effects from it. So it doesn't give you allergies like some antibiotics do. So that's one of the advantages. If you're allergic to penicillin, you can't take low-sec HP7, you might take a bismuth treatment. So if you've got Helicobacter, don't worry, it can be cured. So bismuth and amoxicillin, one of the safest drug combinations with low-sec. So Dr. Warren said I should do a double-blind study. So I did a placebo-controlled double-blind study in Australia in 1985. And what we did, we took patients who had Helicobacter, who had troublesome recurring ulcers, and we gave them 2 treatments. So they either got cimetidine and placebo. So one group got acid blockers plus fake antibiotics, and the other group got acid blocker, cimetidine, plus bismuth and metronidazole, both anti-Helicobacter treatments. And then we healed the ulcer, and then we waited about 12 months and from time to time did an endoscopy to see if the ulcer was coming back or if the patient had a complication of it. And what we found is that if the patient had received the bismuth with metronidazole and the Helicobacter had been eradicated, guess what? The cure rate was 80%. If you just received an acid blocker and no antibiotics and you still had the Helicobacter in your stomach after that treatment, the cure rate was only 20%. In other words, 80% of people had their ulcer coming back after 12 months. So it was pretty obvious that this new treatment was really, really great. And subsequently, another study was done, this time in Austria, not Australia, and that was placebo-controlled, and that's similar, but ranitidine, that's another acid blocker, with amoxicillin and metronidazole, and compared with ranitidine and placebo. So if you look at this study, you see after the ulcers were healed, you just waited, and sure enough, all the patients who had received fake antibiotics had recurrence of their ulcers. So it went way, way down. So less than 10% of people were cured, compared with about 90% of people cured of their ulcer after the Helicobacter had been eradicated. So it was pretty obvious then, and people really believed that ulcers were now caused by the bacteria. So, hey, let's get rid of them. And guess what? Most people who developed stomach cancer, which is, as I said, is very common in Asia, most of those people had Helicobacter for most of their life, causing that inflammation, and we do think that inflammation leads to stomach cancer. So there were more double-blind trials after that. As you see, we studied 100 patients, etc. And then other people did it in Amsterdam in 1990, Dr. Graham in Houston in 1991, and then Henschel, as I showed you, in Vienna. So after that data, other people repeated it, as I said, and eventually there was a consensus conference in about 1994 at the National Institutes of Health in Washington, D.C. So after that, everybody could treat ulcer patients with antibiotics if they wanted to try it out. But the treatments weren't so good, and it was very difficult to see if the treatment worked because you had to pass the endoscope on the patient, take another biopsy. So that's like a $1,000 or $2,000 procedure. And so not everybody could afford it, and everybody was so busy they couldn't double the number of endoscopies that they were doing in their hospital. So it was a bit of a problem. So we needed some simple, accurate tests to diagnose Helicobacter. Firstly, to make it simple for gastroenterologists. You didn't have to have a research lab anymore. And then ultimately to make it simple for your regular family doctor to do the whole thing. And maybe you wouldn't even have to have an endoscopic examination at all. So that was the hope. So this is the answer to the curiosity-driven research idea that I showed you way back at the beginning of the lecture. So how can bacteria live in the stomach? So let me tell you about urease. It's an enzyme produced by Helicobacter. And it was discovered in Helicobacter by Dr. Langenberg in Holland in about 1986. The thing is, though, that of all the bacteria on the earth, Helicobacter produces more urease enzyme than anything else. So it must have a useful purpose, right? And I was looking at the equation there and I said, well, hang on a minute. Here's urea. It's present all throughout your body, in your gastric juice, your saliva and everywhere. So it's in your stomach. And it consists of CO2 with 2 ammonia molecules joined on. And if you have urease enzyme, for instance, from Helicobacter, that would be broken down. It would consume a hydrogen ion. So in the reaction, acid is used up. Takes up a bit of water and generates ammonia and bicarbonate. So you see, we've got acid on this side and we've got alkaline on the products. And so this is a way that Helicobacter protects itself from acid. And so that the curiosity we had, how could bacteria live in the stomach? What do you know? This is the reason. It makes ammonia and bicarbonate and protects itself from acid. So we did further experiments to prove that. And here you see an XY plot. On the x-axis, you see the acidity increasing as we go to the right, which is a lower pH down to 1.5. And we put different bacteria in this brew, which we called artificial gastric juice. And if the pH was 7, for instance, neutral, all the bacteria survived for about 30 minutes, probably for hours. And so the ones we tested was C. jejuni, no urease, Proteus, a little bit of urease, and H. pylori, lots of urease. Anyway, so if you look at what happened, you'll see this one, C. jejuni, after pH 4, as it gets more acidic, the bacteria are killed. So there's about 9 logs of killing. If you look at Proteus, which makes a fair bit of urease actually, but nothing like H. pylori, even Proteus after pH 3.5 was killed. And so after 30 minutes or so, pH 2.5 and less is killed. However, if you put Helicobacter into this artificial gastric juice with a little bit of urea present, you can see the Helicobacter is the dark line here, 10 to the 6.5 of the bacteria persisted. And so you've still got 1 million bacteria per mil living in that gastric juice after 30 minutes at pH 1.5. So that's why Helicobacter pylori doesn't care about all those other bacteria. It's the only one that's going to be living in your stomach. So what happens, we published this paper, and you'll see the urea and the hydrogen ion starts attacking the wall of the bacteria. It breaks down the urea to make bicarbonate and ammonia. So even though the environment has pH 2, inside the bacteria it's pH 7, pH 6, something like that, which is pretty normal for bacteria. And so urease protects H. pylori from acid. So what's the use of this? Well, guess what? If you take a biopsy sample, you can do a rapid urease test. So instead of culturing the bacteria in a very fancy research lab with special incubators, you just take a biopsy and you put it into this gel called Christensen's agar, and you'll see that it generates ammonia and the pH changes, and you see a red color, just like litmus paper really. And you see this is probably an early one, and after half an hour you see these red blotches, and that one, that little biopsy there is no urease, so no Helicobacter. And if you make a concentrated form of that, you can see this is a big red spot from a biopsy just after a few minutes, and a colony of Helicobacter is much stronger even than that. So that was the early rapid urease test for Helicobacter pylori, and it became a commercial test called a CLO test, which means Campylobacter-like organism test, and millions of those tests are sold around the world each year, and generic tests are in every country, and at least 30 million tests are done per annum. However, you still needed to have an endoscopy. So the final thing is, how could you diagnose Helicobacter accurately without an endoscopy? Well, hang on a minute. What about this? What about if we take an isotope of urea? And so there's the urea molecule, and on this carbon, we've got a carbon-14 isotope. That's a label. It's a radioactive label. It's just a tiny, tiny safe amount. And you can use another isotope, carbon-13, which is not radioactive if you want to, but really no difference. And you put that in a capsule, so the patient eats the urea, drinks it on a fasting stomach with some water. If the H. pylori is present, you see that that urea is broken down into CO2 and ammonia. The ammonia just goes into your blood harmlessly, and the CO2 goes into your blood and then through your heart comes out in your lungs. And so about 5 minutes after you swallow the capsule, we can detect that isotope of CO2 in your breath, and you can collect it in a special solution, put it into some fancy kind of Geiger counter, and you see these little counts there. If there's lots of counts, usually more than a few hundred, that means you have got Helicobacter. And if you have treatment, we can do that test again. And if it's back to normal, no counts coming out in the breath, you say your Helicobacter is now gone. And that is just as accurate as a pathologist doing a biopsy. So now every doctor in the world almost could easily do this kind of test, and no need to be a gastroenterologist or have endoscopy. So saving everybody thousands of dollars. And so that's the story of how curiosity-driven research led to the Nobel Prize. And here we are, Dr. Warren and I receiving our Nobel Prizes there at the ceremony in Stockholm in 2005. In the middle, that's my wife, Adrienne. And when you're doing all this hard research, it's a lot of sacrifices for your family. So it's great to have a smart, dedicated person helping you stay in a good mood and succeed with all that hard work that you're doing. I'll just say here that my main affiliations now are with the University of Western Australia, Marshall Lab for Biomedical Engineering, and the Shenzhen University Marshall Lab for Biomedical Engineering, and you'll probably see a few more references to those things in the future. And down here on the right, you'll recognize that this is a QR code for WeChat.
Nice to meet you on air. How are you?
Great. So that turned out to be quite a good lecture. I think people liked it because it's kind of like a long YouTube. People can see all the details of it.
Nice to meet you on air. How are you?
Yeah, I think
great. So before I come to the questions from the audience, can I just ask you my burning question? When you swallow this bacteria, drink it into your stomach, did you ever worry about the consequence of it? Because at that time, there was no effective way of clearing the bacteria. My burning question. When you swallow this bacteria, drink it into your stomach, did you ever...
Hello, do you hear my question?
So we're having trouble with an audio. I don't know whether it's working well now, but
okay, let me repeat my question.
Hear my question?
My question was, when you drink the bacteria into your stomach, did you ever have a second worry about what would be the consequence, because there was no effective cure at that time of the bacteria?
Let me repeat my question. My question was, when you drink the bacteria into your stomach, did you ever have a second worry about what would be the consequence, because there was no effective cure at that time of the bacteria? Let me repeat my question. My question was, when you drink the bacteria into your stomach, did you ever have a second worry about what would be the consequence, because there was no effective cure at that time of the bacteria? Let me repeat my question. My question was, when you drink the bacteria into your stomach, did you ever have a second worry about what would be the consequence, because there was no effective cure at that time? So I'm not sure what the situation with the audio is. I've just turned my speaker off, and I will mute in between. But did I have any concerns about drinking the bacteria? Well, whenever you do anything for the first time, there's a bit of an unknown. And I say to people, it's like taking your first bungee jump. And actually, I'm never going to do a bungee jump myself. But at least you can look at the science of it, and you can say a lot of people have done it and survived, and the ropes are quite strong, check everything, but you still feel a bit nervous when you do it. So it was like that with Helicobacter. I knew by then that about 40% of people in Fremantle Hospital, just visitors or blood donors, were infected with Helicobacter, and so I knew it was very common. A lot of people had no symptoms, so it wasn't always going to lead to ulcers or cancer. And the other thing is that I had taken the bacteria from a patient who I'd been able to cure using some antibiotics and bismuth. So metronidazole and bismuth were given to this patient, and I knew the organism was sensitive to metronidazole. So I had a bit of information, we'd been working for a few years by then, and I was fairly confident that I could eradicate the bug. Overconfident, in fact, because someone else who tried to repeat the experiment in New Zealand was unable to eradicate the bacteria, and he had stomach trouble then for about 3 years afterwards. So there's always the unknown, and it's bad policy. It's not good science to do experiments on yourself because it's not objective. How could you really be certain that the bug was causing your symptoms? Were you just imagining it or had something else? But we did have one thing that was objective, and that was the biopsy. So we had a biopsy beforehand, and then we had a biopsy in 2 weeks later. And we could see the infection, the inflammation, the white cells, and the gastritis had developed, presumably as a result of the bacteria. So I could start from that point, and then the rest of the data I obtained from that research was softer data, if you like. So it turned out all right. I learned a lot, and we created a hypothesis which turned out to be true. So it was 10 years before people really believed it after that. So I'll just unmute you now, and we'll see what happens. And I'll mute my microphone.
There are a couple of people in the audience who ask why not use an animal model, and if animal model doesn't work, is there any other technology like organ on the chips or other technology that will be able to avoid you from drinking the bacteria yourself? Can you hear me? The audio is not working.
Can you hear me?
Yeah. So I have to turn off the speakers. The audio is now working, I think, and it's picking up the audio again from your end and bringing it back to me. So it's a little trouble.
Okay.
But you asked me about could you do it a better way? Well, now we do have animal models, which is gerbils. Mongolian gerbils are quite a good animal model. And the second thing is you can do studies of organoids, which are cultured gastric glands, if you want to look at things like attachment. And you can even do attachment with sort of GMO, genetically modified cells, removing and adding back the different receptors for Helicobacter. So you can go a long way now in vitro, which is much better than human experiments. So we still do some human experiments. We've got some information from that, but mostly you can do laboratory work. If you have a good plan and a direction, then it's certainly going to be worthwhile doing that.
Right. Can you hear me if I ask question again? Do you hear me now? Barry, can you hear me? Well, it's not working. You can hear me? Okay. Well, just one more question before I pass on to the audience to ask you directly. You mentioned also that despite your findings, your paper was rejected and nobody believes that a bacteria can survive in the stomach. So what was your feeling at that time, and what is the right attitude when what you firmly believe in was rejected by the world and your paper is not acceptable? What was your feeling at that time, and how would you advise young people to deal with this?
So I can, there's some feedback coming in, but don't worry about that. I've turned off my speaker. So when the paper was rejected, Warren and I had already been testing our own hypotheses. So when you're in research, you want to try and be objective, and you want to find out why people might not believe your new discovery or new observation. And then you should test your own hypotheses critically, because instead of designing experiments which prove that you are right, you should try to design experiments which prove that you are wrong. It's much easier if it's a false observation or false result. It's much easier to prove something is wrong. It's very hard to prove it's right, and you only succeed with a new paradigm, if you like, when you've tried to prove it wrong many times. And this is what the scientific process is. Scientists are going to try and prove that you're wrong. And you should do that yourself before you really start trying to promote your new discovery. So, yeah, I've tested that and we found this or that. And so you should try to knock down your own hypothesis several times in the lab before you actually move on to the next step, rather than just coming out with it and saying, I want to get an early publication. Obviously, you can do a very small publication, like a local meeting with a poster and discussing it with your peers. That's very, very important and very useful, and it does fix the timeline of the discovery. So that's important, but you really need to be able to test your own hypothesis quite a lot before you move on. And so I had done that. So we were not particularly worried about all the criticism that we might have and people not believing this idea. And that's why we were trying to do animal experiments as well as human experiments.
But when will you say enough is enough and you will give up, you will not do it anymore? Can you hear my question? When will you say stop?
Well, I notice I don't have as much energy as I used to, and I try. The secret is to find good students, PhD students, postdocs who maybe have got their own research skills that want to work in different angles of it, and then they are doing the hard work nowadays. I've got other activities which I also do, so I'm not working like 6 days a week on the same Helicobacter project. But because of a long history of observations in clinical medicine and in laboratory research related to Helicobacter, I can often see flaws in the experimental technique, or say I know that this has already been tested. So I think you can accelerate the process a little bit if you've got a couple of senior people overlooking things in the lab. So I still have that role. I probably continue to do that for another 5 or 10 years, and then I might say stop.
Okay, there is a lot of questions from the audience. Some are very scientific. Some ask you, how does H. pylori taste? I'm going to ask Lo Yi Choi to ask you some questions, because she actually asked quite a few of them. Lo Yi Lewis Choi, are you there? Hello, Lo Yi Choi. Can you come in? What's that? You have to stop. Well, she actually asked you, well, with so many people infected by H. pylori, but only a small number of them develop ulcers and cancers, why is that so? What contributes this difference in the outcome of the infection?
There's 2 or 3 things. Firstly, to develop an ulcer, you do need a fairly strong acid level, and that has happened more in the 20th century. Prior to that, nutrition is not so good, and often in Asia, the nutrition was not so good, so that people in that I tested actually in Brazil were only producing half as much acid as Americans, and so that means that they were unlikely to get ulcers. The low acid state, however, and the severe gastritis that comes from lifelong Helicobacter is a risk factor for stomach cancer. So people that weren't getting ulcers were getting stomach cancer. So they're the things that would be affected by your lifestyle and the quality of your diet. And then the next thing is some Helicobacters are more inflammatory, so that if you have one of those Helicobacters, you're more likely to get more inflammation and more disease. So all those things interact. Luckily, Helicobacter, like a successful bacteria, has 80% of people asymptomatic. They just pass it on. And you don't even know that you have it. So nowadays, it's kind of a screening test. When you have your thyroid function done at age 40 or 50, you might probably have a Helicobacter test of some sort in a lot of countries now. Sorry about that echo. It's fixed, but I realize it was a tricky issue.
Yeah, one last question from Japan, Barry. This is a Japanese doctor, I suppose. He asked you, what is our next battle? Now H. pylori has been eradicated, and there's no more ulcer. And what do you think is the next battle against, different types of diseases in the stomach?
So apart from Helicobacter, the main problem is gastroesophageal reflux, I suppose. And so we have got the medications to combat that, the proton pump inhibitors. So we're very lucky these days not to have quite so much untreatable stuff going on in the stomach. And so one issue is, can you predict a person who has got a cancer risk in the stomach? So people looking at things like the microRNAs and different types of histology in the gastric mucosa. So that's underway. That'll be solved probably in the next few years. But in the year of COVID, the second or the third year of COVID, I think we need to look again at what we do with infectious diseases. And we worried about Omicron, but really all common colds and many of these little viruses that we catch all the time are so infectious, and no one has really tried to solve that problem. We all spend a week being unwell each year with a cold, perhaps. Our productivity goes down. And, we don't think about that like we do with COVID. It's not going to kill anybody, but certainly someone's walking into your office, they're touching your laptop computer, you're picking up the microphone, opening the door. You're going to be picking up viruses all the time. So obviously surveillance for all these different little viruses and rapid production of vaccines is where we're going to go. And at the moment, everything's still having needles. But the future is, I think, that we will develop an oral vaccine. Oral vaccines with a production time of about 3 months, and people can buy them in the supermarket. So that is the holy grail with vaccines. And you take the doctors out of the equation. People can do their own home test. They can take the latest oral vaccine, different flavors, etc. And so one of the angles I've been working on for years is using H. pylori, something about H. pylori to get antigens into the gastric mucosa or into the intestinal mucosa, because you do develop antibodies against Helicobacter and it's in your stomach. So at least your immune system thinks it's a pathogen, tries to react against it. So you might be able to use one of H. pylori's tricks to develop oral vaccines. So that would be the next generation of vaccines after RNA vaccines, I think.
Okay. Professor Marshall, thank you very much for your time and your inspiring talk. I think time is up, and we have to say goodbye here. Hope to see you again very soon.
Welcome to this session. Our first speaker is Ling Chen. Ling Chen is currently a PhD student in the Department of Mechanical Engineering and Sustainable Manufacturing at City University of Hong Kong. She obtained her bachelor degree in Process Equipment and Control Engineering in 2019 from Xi'an Jiaotong University. During her undergraduate studies, she has been a visiting student at National University of Singapore and a research intern at University of California, Los Angeles. Ling Chen has won many awards such as Hong Kong Tech 300 Seed Fund, UCLA CSST Award, and a Bao Steele Excellent Student Scholarship, which was awarded only to top 1% of students of her cohort. Today, she's going to present us her exciting research about nature-inspired fog harvesting system for power generation and freshwater production.
Hello, everyone. I'm Ling Chen from City University of Hong Kong, and my supervisors are Stephen Wang and Zuankai Wang. And today, I'd like to share with you a completely new energy solution, a fog-powered generator. We all know that moisture resources is everywhere around us in the air. And it's estimated that the moisture resources in the world is equivalent to around 5.2 billion Olympic-sized pools that full of water. And especially in coastal regions, like in Hong Kong or in Singapore, the annual mean relative humidity could be as high as 80%. And in some special time in mountainous or coastal regions, the humidity can even go up to 95 or 100%. Today, some scientists and engineers have tried to harvest the fresh water from the fork, but almost no one have tried to utilize the fork to generate electricity. And one day we just found that when the fork condenses on the meshes and drops down, there should be energy stored in the dropping water. So why don't we just harvest it? So we designed these fork-powered generator systems, and we coupled a droplet energy generator with the fork harvester to harvest the fresh water and electricity at the same time. And the electricity could be further used to power the IoT devices like electronics, sensors, or smart illuminations. And this is the first prototype. The fork flows through the fork harvester and condenses on the superhydrophobic meshes. And then the droplets will slide down and impinges the surface of the droplet energy generator to generate electricity. And the electricity will be used to lighten the LEDs or power the IoT devices. And finally, the fresh water will be collected in the reservoir. And later, I will introduce you from the two sides for harvesting and power generation. Well, the meshes are the most common structures that are used in the world to harvest fork because they have high efficiency and very low cost. And we made some modifications on the meshes that inspired by nature. For example, the fibers are inspired by the spider webs, and the artificial tapers are inspired by the cactus spine. And they both improve the fork harvesting efficiency. And we also apply some chemical coatings to make it superhydrophobic. That is inspired by the waterproof lotus leaf, so it can have the anti-fouling and self-cleaning functions. And you can see that because there are tapers microstructures on the meshes, so the tiny fork droplets can condense very quickly and easily on the meshes, and the droplets can also transport directionally. And you can also observe there are three comparisons between the conventional plate and the meshes for harvester and our specially treated harvesters. And you should observe that the water droplets detaches very quickly on our specially treated meshes. And when there's contaminations, it can also very fastly clean it. And comparing with the other conventional fork harvesters, our latest inspired fork harvesters have 3 times higher efficiency than the other ones. And you might be very curious about how we could transform the water to electricity. Well, you should know the tribal electrification phenomenon, which happens in our daily life when you rub 2 different materials like the glass and the fur, then they will have opposite charges on it. And when you are in a dry environment and your body is easily to have charges, and you can feel that when you touch other things. So when the water droplets drops down in the air, then it will have frictions with air, and when it impacts with the surface, the collisions will make it to have a large amount of charges. So that's how we make use of the tribal electrification phenomenon to generate electricity from the dropping water. And this is the droplet energy generator that we designed, and its structure is made of the electrode, a PTFE film, and the ITO film. And when the droplet impinges on the PTFE film, it will be electrified to have the negative charges, and the ITO will be induced to have the positive charges, and we collect the ITO with the electrode, and when the droplet is sprayed to contact with the electrode, then the whole circuit will be closed and the current will be produced, and we can have electricity through this way. And this is the performance of only one droplet, and you can see that it can generate electricity up to 200 volts. And we have conducted experiments in around a month, and it shows very outstanding reliability. And we also upgrade our prototypes and successfully demonstrated in our laboratory. And it successfully lightens the LED lights. And except for this, we can also collect the droplet energy generator with the rectifier and capacitor to store its energies and for further use, like to power the calculator or power the sensors. And hearing of this completely new techniques, the Hong Kong government department EMSD reaches us to ask us to help them make a large-scale droplet energy generator, and it made up of 100 DEGs, and now it is placed in the fountains in front of the EMSD buildings. And we also scaled up our prototype and changed its overall structures to semicircle to optimize its aerodynamics efficiency. And in the future, we aim to do more trials at the Hong Kong Island or the Taimao Mountain, etc., to provide fresh water and electricity for the Hong Kong local citizens. And those trials are supported by the multiple Hong Kong government department. And finally, we anticipate that our fog-powered system has multiple applications. For example, for now, there are more than 50 billion IoT devices are collected in the world. But if such devices like sensors or electronics are put in like remote areas or harsh environments, it might be impossible for human beings to go to those places to recharge or replace the batteries. And it might cause very serious environmental problems. But if we can couple our fog-powered system with such IoT devices, then it could sustainably provide power for the IoT device. And that's all for today's talk. Thank you very much for your kind.
Nice talk. This talk now is open for questions from the floor. So if you have questions, please type in the chat box and raise your question. But before we have the questions from the audience, maybe I can first start with some questions. So I'm a chemical engineer by training. So I listened to your talk. I heard this word of condensation. When I hear condensation, I feel very anxious because for condensation, we refer it to vapor condensed to the droplet liquid. And there's a huge latent heat being released. So can you clarify whether the fog condensed to the water droplet, is this a condensation process or it's just a collection of water droplets?
Thank you. And well, in our research, I think because we use the matrix and has spatial microstructures, and it's mainly is that the very small tiny fog droplets, and they combine and they collapse on the structures, and they combine and grow up into the water drops. And I think that's not the condensation process.
So there's no phase change Basically,
Yes.
you collect. Okay, thanks for the clarification. So now the questions are from the audience. So the first question is from Clemens. Are there electricity generator pricey? Are the electricity generation pricey or costly? Do you need many resources to produce them?
That's good. That's a good question. Actually, our generator is very cheap because it only consists of like IoT glasses or a metal substrate or a PTFE film, and those materials or the copper or the coppers, and those materials are very cheap. Actually, the cost, it only costs around less than 3 Hong Kong dollars for one piece.
Okay,
So it's
that's cheap. Thank you. The second question is, Dr. Chen Ling, may the application be extended to atmospheric water harvesting?
Yes.
Okay. So the short answer is yes. Okay. I guess we have one more. We have time for one more question. Wondering whether your device can be used in Africa region to generate electricity at night, and at daytime the water collection can be used to generate electricity or used for clean drinking water.
Well, actually, previously we are researching the high harvesting frog in very high humidity environment, but for now we also consider about harvesting the moisture in the low humidity environment using like the other absorbent. Also, it's anticipated that in the future, we might also harvest the fresh water in the daytime and use that the water to generate electricity using our droplet energy generator. And
right. So it even works in Africa, where the moisture is not very high in the atmosphere.
Yes, actually, for now, we are developing a material that can harvest moisture that in humidity that as low as around 40%.
Okay.
So that could work.
Sounds good. Thank you. We do have time for a very short question, last question. So there's this question from audience: how long we can continuously power the IoT devices, or do you have any power storage in your system?
Well, I mean, the first, okay, could you repeat that? Sorry.
How long you can continuously power the IoT devices? How long? Yeah, do you need the storage device?
Yeah, actually, we leave them for now. For now, we use a circuit that we transform the electricity that generated by the generator and store that in a capacitor, and then we use the energy from the capacitors to power the IoT devices. And we are trying to solve this problem and trying to try to power the devices directly. It's not solved for now because the one droplet, because the power generation process is not a continuous process, so we need to store the energy first.
Okay. Although we have more or less reached the time limit, but there's a burning question. This is also something that I want to know. Do you expect the need for huge amount of land to deploy your technology? This is coming from Singapore, where the land space is a very limited resource.
Actually, I think this is the advantage of our generator, because we can design a multi-stage generator. I mean, we can use droplets that repeatedly, and we can put the generator in multi stages, and that can save a lot of space. And we can couple our device with different buildings. We can put that on the rooftop of the buildings or in the mountains, and we can design different prototypes and use that.
So it's not really.
The second speaker is Dr. Xingrong Ho. He is currently a research fellow at Japan Society for the Promotion of Science, JSPS, Institute of Multidisciplinary Research for Advanced Materials, Tohoku University, Japan. He obtained his PhD degree from the Graduate School of Environmental Studies of the same university. Earlier than this, he did his bachelor and a master's program in the Department of Resources Engineering, National Cheng Kung University, Taiwan. His research interest is on carbon capture and utilization, more specifically using cement and concrete wastes to capture CO2. He has published around 10 journal papers in Tier 1 journals and filed 3 patents. In 2021, he received the Research Fellowship for Young Scientists from JSPS. We look forward to his presentation on innovative CO2 utilization via mineral carbonation of alkaline waste.
Hello, everyone. I'm Xinjong Ho. I am postdoctoral research fellow granted by JSPS, work in Tokyo University in Japan. And it's my pleasure to attend this summit, and my research topic is carbon capture and utilization via mineral carbonation of alkaline waste without CO2 purification and pressurization. Okay, so here goes to the introduction part. Global warming is one of the most urgent environmental issues in this century. CO2 emission is one of the main factors causing this issue. So to mitigate and alleviate the global climate change, Paris Agreement is ratified in 2015. It is one of the most biggest agreement for CO2 emission reduction. It's that holding the increase in the global average temperature to well below 2 degrees Celsius, preferably to 1.5 degrees Celsius compared to pre-industrial levels. Besides, carbon neutralization, which is equivalent of net zero emission, is the main strategy to remain compliant with the Paris Agreement. Several countries and unions like USA, Japan, and EU have progressed toward this goal by 2050. And carbon capture and utilization is the concept of the utilization of CO2 as feedstock in various applications. And it is regarded as promising technology contributing to CO2 emission reduction issue. Advantage, the potential of economic income, social acceptance, and many applications and processes can be utilized. And in my research, I study mineral carbonation. In mineral carbonation, alkaline rock or waste containing calcium and magnesium will react with CO2 to form carbonate, which is calcium carbonate or magnesium carbonate. The advantage of mineral carbonation are that it is spontaneous reaction. As the left-hand figure shown, the change of gas-free energy is over zero when CO2 most of materials, which indicates that the high energy input is required. However, in mineral carbonation, the change of gas-free energy is negative, which means reaction is spontaneous reaction and means that the reaction is possible to develop using fluid gas without CO2 purification and pressurization. And second advantage is stable product. Carbonated product compared with other CCU technology application is more stable. And third is it has relatively huge potential. Compared with other application products, the market size of calcium carbonate is huge. Therefore, this process is not limited to market demand. Hence, it is possible to develop CCU without CO2 purification and pressurization, which is costly and high energy input while mineral carbonation. Here, this This technology still has some research gap, and the main research gap is slow reaction speed. So we would like to investigate to enhance the reaction with less power consumption. And the concept figure in this research, the exhaust gas and generated solid waste from industry are used as raw material in mineral carbonation technology to form a carbonated product. And CO2 utilization and carbon recycling and the waste reuse and recycling can be achieved. Based on this concept, this research can contribute to the goal of carbon neutrality and circular economy. Okay, so in this research, we investigate direct aqueous carbonation of concrete fines generated from aggregate recycling. To move the cement and concrete industry toward a circular economy and reduce its environmental impact, recycling of waste concrete is critical. And concrete is a mixture of hydrous cement accounting 30% and coarse and accounting 70%. After aggregate recycling of waste concrete, the recycled aggregate can be recycled back to cement production. However, the generation of concrete fines as byproduct becomes a problem. Advantageously, the concrete fines are almost free of aggregate contamination, which makes them promising candidate for carbonation with low energy input. So in this study, we explore the potential of concrete fine in direct aqueous carbonation. In this study, we investigate 3 types of concrete fine. Fines A is generated from low-class aggregate recycling process from demolished concrete. And fine B is generated from high-class process from solidified return fresh concrete. And synthetic concrete fines are prepared to simulate actual concrete fines from aggregate recycling process without aggregate contamination. And the characterization have been done as the table and figures. The calcium content and impurities such as silicon, aluminum, and iron have been confirmed. And to confirm the carbonation potential, the effective calcium here is determined by TG and calculated. The fines A and fines B have the greater number of calcium carbonate compared with synthetic concrete fines. The reason of the difference of the concrete fines are because of the different process and different source. It is worth noting that the effective calcium in fines B 6% indicates that fines B have good potential to be used in mineral carbonation with low energy input. Here is the main reaction step in direct aqueous carbonation of concrete fines. This reaction is based on 3 main steps of reactions. First, calcium extraction. The concrete fines are dissolved by water and the calcium is extracted as calcium ion. Meanwhile, the hydroxide ion will be released. Second, CO2 dissolution. The gas state CO2 will be dissolved into aqueous phase as carbonic acid and become carbonate ion. At the same time, the proton will be released with carbonate ion. And when the pH is higher, CO2 dissolution is favorable. Third, calcium carbonate precipitation. The dissolved calcium and carbonate ion will react together to form precipitate calcium carbonate. And it is worth mentioning that all of the reaction is concurrent, and the water can be used repeatedly. And the bottom figure is the experimental setup in this study. Because of limited time, I introduce in brief. Here is the result part, and we investigate direct carbonation of concrete fine in detail. and various parameters have been studied. For example, time variation of calcium concentration and other impurities concentration not shown can understand the situation of calcium extraction and calcium carbonate precipitation. And the time variation of pH can evaluate the condition of calcium extraction and CO2 dissolution. And time variation of CO2 concentration can calculate the CO2 uptake, and the time variation of degree of carbonation can understand the degree of we can realize the relationship of CO2 captured in water and in solid. And by particle size distribution analysis and TGA, we confirm the reaction mechanism are solidification and particle collision during direct aqueous carbonation. And here is the summary of this study. This is the simple flowchart of this process. The waste concrete is treated by aggregate recycling process, and 70% of aggregate is recycled as recycled aggregate, and 30% of hydro cement as concrete fine are utilized in study. And the flue gas level of CO2 is thus fully treated by direct aqueous carbonation of concrete fines. And the CO2 uptake efficiency of concrete fines is high. It proves that the concrete fines are promising candidate for developing carbonation with low energy input. And the carbonate products are characterized in detail and meet the requirement of various utilization. And the interesting future suggestions are listed. The application potential of carbonated products should be developed, and the process for relatively inert alkaline waste should be developed. And the detailed results can be found in below reference. At final, I would like to thank to Professor Atsushi Itsuka for his kind supervision, and any questions and comments are welcome. Please feel free to contact with me by email or directly. Thank you for your time and attention.
Thanks, Sinjong, for your very nice talk. I enjoyed your talk. This is a very important topic in carbon capture and utilization. So now this talk is open to the questions from the floor. Are there questions? All right. There's a question from the audience. Within the industrial applications, is there potential of direct carbonation of concrete fines under atmospheric pressure for CO2 utilization without CO2 pressurization?
Okay. Here, because the potential.
Is there a potential for industrial application of your technology?
Okay, yeah. Actually, in our study, we capture CO2 by the concrete fines generated from aqueous recycling process, and the CO2 is captured as the carbonated product. And however, the carbonated product purity in direct aqueous carbonation process is low. So we will like to develop this carbonated product as the environmental purification agent. And actually, we are studying in this research, and we want to explore the more industrial application. For example, we want to use this carbonated product to absorb the heavy metals in environmental issue, and this can increase the economic income in this total process, and also can extend the potential for industrial application.
Right. So if I understand you correctly, currently the application is more towards applications such as water treatment rather than recycling it back to be the concrete building material.
Oh, yeah.
Right. So maybe it's because, sorry. So it's because of the purity of the product after the mineral, after carbonation.
Simply, yeah, they have two ways. The simple way is just back to cement and concrete production. It is very simple and it's possible. And now we are trying to explore the new way, is chemical recycling process. Yeah.
I see. All right. We have more questions coming in. The second question is, would this CO2 carbonation affect the mechanical strength of the concrete compared with the original or ordinary concretes?
It is interesting question. In my study, I'm not I'm not study well in the strength of concrete because as I say, I utilize the carbonated product go to capture to remove the heavy metals. So I didn't study to reuse back to concrete and cement production. However, I have studied some papers and some research. They increase the strength of concrete if they use the ideal percent to replace the ordinary cement or ordinary concrete.
Okay, thanks. Is there a problem for this technology for large scale? If yes, what are the main factors?
Okay, so this is also a very excellent question. In our concept, we use this technology is basically for small and medium scale industry. They have many factors, but for me, in my opinion, the main factor might be the source. Our source is based on the flue gas and also based on the waste. And we should consider the balance of the source, not the waste. For example, in our waste is concrete fines, but in many seasons and in many seasons and many countries, the production is not the same and it's not stable. So, and the flue gas, the percent of purity and concentration is also not stable. So, sorry. So, for my understanding, in our technology is beneficial into the small and medium scale industry.
Mm-hmm. Okay, we would like to ask one last question. How much extra energy is required for this process? Does the carbon capture offset the carbon footprint of the energy requirements of the process? Or does the technology need to be made more efficient?
This is also a very important question. The energy concern is always the energy problem is always the main concern in mineral carbonation process. Mineral carbonation process is slow reaction speed. So in past studies, they usually use the high required energy to enhance the process reaction speed, to enhance the kinetic. But in my concept, we utilize the concrete fine, which is very high calcium content and without aggregate contamination. It means the calcium, most of the calcium is calcium oxide, which can be easily to react with CO2 to form calcium carbonate. So in my opinion, yes, if we can use a little large energy, we can enhance the reaction. But if not, we still can do this process smoothly. And the carbon capture offset the carbon footprint of the energy requirement. Actually, in my papers, we have a simple calculation, and we believe it can be. Thank you.
Thank you. Thank you very much. So with this, we end this talk. Thank you, Xingrong, for your nice talk, and all the best to your future work.
Thank you very much.
Dr. Jun Li. She is currently a postdoctoral fellow in Department of Mechanical and Automation Engineering, the Chinese University of Hong Kong, where she also finished her PhD degree in 2019. Her bachelor degree was in Chemical Engineering from Tianjin University. Her research expertise is on redox flow battery and lithium-sulfur battery. She has published several high-impact papers in top journals such as Nature Energy and Advanced Materials. She received the Outstanding Thesis Award from the Faculty of Engineering, Chinese University of Hong Kong. Today, she's going to share with us her exciting work on energy storage using redox flow batteries and lithium-sulfur batteries.
Hello, everyone. I'm Zhe Junli from the Chinese University of Hong Kong, and now we are going to look at the materials design and mechanics investigation of advanced sulfur-based batteries. Owing to the greenhouse gas emissions, our planet is warming up rapidly, which leads to an increasing frequency of the extreme weather disasters. So what is the sources for CO2 emissions for the climate crisis? As is shown here, over 70% of the CO2 emissions come from the energy consumptions for industry, transportation, and residential buildings. However, we also have opportunities. The levelized cost of energy of solar and wind keep declining in the past decade to be competitive with conventional fossil fuels. Therefore, there is an urgent need to integrate these clean energies into future clean electric grids and the decarbonization of transportations. However, their intrinsic instability and intermittency limits the grid penetration, rendering the energy storage system a critical enabler to fulfill this clean grid landscape. And among various energy storage technologies, batteries provide high design flexibility and play an increasingly important role in various applications. And currently, lithium-ion batteries takes 90% of the global battery market, but still suffers from challenges like low energy density, poor scalability, high cobalt cost, and concerns of their safety and earth contamination. Sulfur, on the other hand, is one of the most earth-abundant elements with ultra-low price and high energy density, rendering sulfur-based batteries a cost-effective and sustainable alternative to conventional lithium-ion. Therefore, our work focuses on resolving the challenges suffered by the sulfur-based batteries in order to promote a sulfur-powered energy storage landscape. So first, let's start with sulfur-based batteries for grid-scale application. The future clean grids needs long-duration energy storage, and why? And in this renewable generation plots in Germany, the typical discharge duration for lithium-ion batteries are only 4 to 6 hours, far from the demands to fill the energy gaps of 10 to 100 hours shown here. And using 10 times more cell packs are too expensive for the peak shaving. This is also the cases when extreme weather disasters happen. Therefore, long-duration energy storage with discharge duration over 10 to 100 hours are highly desired to increase the penetration of the renewable economically and improve the security of the grids under the extreme weathers. And random flow batteries are one of such technologies with high design flexibility. As is shown here, the power of the system is decided by the cell stack, while the energy is determined by the volume of the electrolytes. Therefore, one only needs to add additional amounts of electrolytes for longer durations. The commercialization of the most well-developed all-vanadium flow battery are greatly challenged by their high capital cost and low energy density. However, polysulfide is promising nickelite for a flow system. We have first designed a polysulfide iodide rel flow battery with lower chemical cost but higher energy density compared to vanadium flow system. In this work, we have demonstrated one of the highest energy density and reviewed the reversibility of both electrolytes for battery operation. However, polysulfide-based flow batteries are greatly challenged by the crossover and uncontrolled water migration through the commercial membrane. To deal with these long-lasting problems, we have further designed a charge-reinforced ion-selective membrane, which is GYSS, by simply coating a polymer-bonded carbon on the surface of membrane. This can effectively repel the crossover and mitigate the water migration. So first, the strong absorption ability of polysulfide and polyiodide in the mesoporous carbon layer lead to a strongly negatively charged surface of membrane, which can effectively repel the penetration of both ions and significantly reduce the self-discharge rate. In static cell, operated for 1,200 cycles in 2,000 hours, a negligible capacity decay was observed, which is equivalent to a shelf life of 15 years. And to specify, this is the most stable polysulfide-based system ever reported. We have further confirmed the scalability of the GYSS strategy in a scaled-up flow prototype, and over 80 days cycling, no capacity decay was observed. And this unprecedented high stability is further related to the well-regulated electrolyte migration. From molecular level, we have applied the in situ FTIR and solid CMR to show that the dynamic movements of water is better controlled in GYSS versus N17. And this can be further explained by a much smaller water cluster sizes in GYSS structure. And finally, our techno-economic analysis of the levelized cost of storage further reveals that the GYSS-enabled PSIB offering an economical pathway for long-duration energy storage in future carbon-free electric grids. And now let's move on to see sulfur-powered decarbonization of the transportation. And high energy density and safety are two critical requirements for batteries used in electric vehicles. And since 19th century, the energy density of batteries increased rapidly from lead acid to lithium ion, but is still far from the demands for personal cars and let alone the heavy-duty vehicles or aviation. Therefore, we always need new chemistry to further boost the energy density, like lithium-sulfur batteries. The energy density of lithium-sulfur is 6 times that of lithium-ion, with great cost advantages. In addition, lithium-sulfur also improves the safety and eco-friendliness versus the chemistries used in lithium-ion. However, they also suffer from many challenges, including low sulfur utilization ratio, poor durability, and breakability. And all of them are closely related to the nucleation and growth process of lithium sulfide during discharge. But in-depth mechanism understanding of this process remains unclear. First, we have reviewed that the quasi-equilibrium potential for lithium sulfide nucleation is determined by the donicity of electrolytes. With the increase of donicity, the lithium ions are better solvated, getting softer to stabilize the soft base polysulfide, thus lead to a lower initiation potential for lithium sulfide nucleation. Next, we also establish a quantitative model to correlate to solvent properties. And for low donicity electrolytes, one should increase the lithium sulfide solubility for higher sulfur utilization ratio, because the surface diffusion of lithium sulfide is the governing step for the 2D growth observed here. For high donicity electrolytes, on the other hand, one should reduce the viscosity of the electrolyte. Because the diffusion of polysulfide precursors are the governing step here for the 3D growth in high donicity electrolytes. And based on these understandings, we correlate the three most relevant solvent properties to sulfur conversion efficiencies and identified a novel and more efficient solvent, propionitrile. The established methodologies has also been successfully applied in the catalyst design. We have found that when we increase the electronegativity of the nonmetal elements from borate to oxide, both lithium sulfide electrodeposition kinetics and the sulfur utilization ratio keep declining, which is also the trend for other metal-based catalysts in literature. This trend can be explained by a much stronger chemisorption of polysulfide in titanium borate compared to titanium oxide from both UV-Vis and XPS results. And we concluded that the electronegativity of the nonmetal elements as a critical descriptor for the catalytic efficacy in catalyst design in lithium-sulfur batteries. And in summary, we have invented the first low-cost polysulfide iodide rel flow battery and further developed an efficient membrane strategy to achieve industrial relevant cycling stability for long-duration energy storage in future clean grids. And lithium-sulfur batteries are promising for the decarbonization of transportation. We have established a quantitative model which is effective in guiding the regional developments of electrolytes and for highly efficient system. And finally, I would like to acknowledge my supervisor and all the other group members during my research life. And that's all for my sharing, and thank you for your attention.
Thank you, Zejun, for a very exciting talk. It's really exciting work, and I enjoy your talk. We are opening this talk for the questions. So the audience, if you have questions, please type in the chat box. Perhaps I can ask the first question. So in your polysulfide-based redox flow battery work, you have already solved this crossover and water migration problem, and the stability has been enhanced greatly. So my question is this already close to commercialization, or are there more challenges to be solved? You are muted.
Currently, we are working on the commercialization of this system to file a patent or to do some improving work to the fabrication of this membrane in a large scale. So I think it is very close to the commercialization, and considering its low cost and readily applicable for the future system. Yeah.
That's great. So have you started talking to some companies, some commercial collaborators?
Yes, my supervisor has started a company for red flow batteries. So currently we are collaborate with many companies to improve this work. Yeah.
Right. So may I also know, with this technology, what kind of vehicle or transportation application you are looking at, whether it's on the road or aviation or some more futuristic applications?
Well, for red flow batteries, we always use it for the grid scale application. For example, in large buildings and some power grids. So it is not always used in your electric vehicles.
I see.
Yeah. So lithium sulfur batteries are promoted for the electric vehicles. because it's a high energy density. Yeah.
Okay, understand. All right, so are there questions? So far, I don't see questions yet. All right, so you also mentioned that you have done the techno-economic analysis. So in your techno-economic analysis, what is the scope of this analysis? Do you start from the renewable energy all the way to the end, the storage and utilization of the electricity?
The levelized cost of energy takes the cost from its investigation to the end of life. So we do this because sulfur is quite cheap, according to our opinion. So we would like to know whether this technology can compete with other commercialized system for grid-scale applications. Since for long duration energy storage, it needs to be very cheap to be comparable to the pump hydro or other kinds of methods. So this is our perspective for doing this. Yeah.
All right, thank you. So we have questions from the audience. So the first one is, I'm wondering whether about the durability of the lithium sulfur battery and the main issue to cause the degradation in the process. What's the main issue? Yeah.
For lithium sulfur batteries, I think it comes from the sulfur, the cathode side. The sulfur and the lithium sulfide are two end products, but they are all insulating. So many dead sulfur will generate during your long-term cycling. So for the durability, I think you should always resolve the challenges faced by the cathode side, and to find some more efficient electrolytes and the electrodes catalysts. Yeah.
All right. The next question is related. So Dr. Lee, I would like to know the definition of the durability of battery. In other words, how do we measure and compare it?
Well, the durability mainly has two aspects. The first one is its cycle life, so which means that how many cycles it can run over its total life. And the other aspect is the calendar life, which means how long what's the calendar time it can run over its life. So these two aspects are all very important for batteries. Yeah.
Okay, thank you for answering all the questions, and it's time's up. Thank you.
Thank
you.
you.
Wish you the great success in your future work.
Thank you.